Hello and welcome back. I'm so glad you're here tonight. If you've had a long day, if your mind has been racing through tasks and worries, lists and obligations, this is your time to let all of that go. For the next while, we're going to travel together, not through the stresses of daily life, but outward, far outward, to a world so vast and strange that it makes our earthly concerns feel small and distant. Tonight we're visiting Jupiter. Before we begin our journey, if you enjoy these explorations through the cosmos, if you find comfort in drifting off while learning something new about the universe, please consider subscribing to the channel. It helps me continue creating these late-night voyages through space and science. And with that small piece of housekeeping complete, we can truly settle in. Jupiter, the king of planets, a world of storms that have raged for centuries, of moons that could be planets themselves, of mysteries layered so deep that even after decades of spacecraft visits, we're still only beginning to understand what this giant truly is. Tonight, we'll explore 100 facts about Jupiter. Not rushed, not frantic, but at the pace of someone drifting toward sleep, letting each idea settle gently before moving to the next. So adjust your pillow. Let your breathing slow. Feel the weight of your body sinking into the mattress. The universe is vast, and Jupiter is waiting. Now let's begin. When we look up at Jupiter in the night sky, and you can see it with your naked eye, a bright, steady point of light that doesn't twinkle quite like the stars, it's easy to forget just how enormous this planet truly is. Jupiter is so large that if you could somehow hollow it out, you could fit every other planet in our solar system inside. Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, all of them, tucked inside Jupiter's volume with space left over. Not just a little space, mind you, but enough room that you'd still have gaps between the planets. To help you picture this, imagine Earth as a grape sitting on a table. Now place a basketball next to it. That basketball is Jupiter. The difference in scale is almost absurd, almost impossible to hold in your mind. We think of Earth as substantial. It contains oceans and continents, mountains that pierce the clouds, canyons that plunge miles deep. And yet, compared to Jupiter, Earth is barely a marble. Jupiter contains more than twice the mass of all the other planets combined. It's not just the biggest planet in our solar system. It's so much bigger than everything else that it almost seems to belong to a different category entirely. This is the world we're visiting tonight, a world where large becomes an understatement, where the familiar rules of planetary existence stretch and warp into something extraordinary. As you lie there, imagine that basketball, sitting in darkness, swirled with colors, spinning faster than any other planet, hosting storms larger than Earth itself. We'll get to those storms soon enough. For now, just hold on to this. Jupiter is vast beyond easy comprehension, and we're about to explore what that vastness contains. Here's something that might seem contradictory at first. Jupiter, for all its immense size and gravitational power, is made mostly of the lightest elements in the universe, hydrogen and helium. The same hydrogen that lifts balloons at birthday parties, the same helium that makes voices squeaky when you inhale it. Jupiter is roughly 90% hydrogen and 10% helium, with just trace amounts of other elements scattered throughout. This composition tells us something profound about Jupiter's nature. It's not a rocky world like Earth or Mars, There's no solid surface to stand on, no ground beneath its clouds. Instead, Jupiter is essentially a failed star, a ball of gas that never quite accumulated enough mass to ignite nuclear fusion in its core. Stars are born when clouds of hydrogen collapse under their own gravity, becoming so dense and hot that hydrogen atoms begin fusing into helium, releasing tremendous energy in the process. Jupiter has the right ingredients, the same recipe as the Sun. It just doesn't have enough of them. If Jupiter had been about 80 times more massive, if during the formation of our solar system more material had fallen into its gravitational embrace, it might have ignited. Our solar system could have been a binary star system, with two suns orbiting each other. Earth would have existed in a very different universe, but Jupiter fell short. It became something in between. Not quite a star, but far more than just a planet. A giant made of the universe's simplest building blocks, held together by gravity so intense that deep inside, those simple elements transform into something strange and exotic. We'll get to that peculiar interior soon. For now, rest in this thought. Jupiter is a reminder that size doesn't require complexity. Sometimes, the biggest things are made of the simplest ingredients. Time moves differently on Jupiter. While Earth takes a leisurely 24 hours to complete one rotation, one full day and night cycle, Jupiter spins so quickly that a day there lasts only 9 hours and 56 minutes, not even 10 hours. Think about that for a moment. If you were somehow floating above Jupiter's clouds, you'd see the sun rise, arc across the sky, and set again in less time than it takes to sleep through a single night here on Earth. This rapid spin has consequences. When something as massive as Jupiter rotates that quickly, centrifugal force, the outward push created by the spinning, causes the planet to bulge at its equator. Jupiter isn't a perfect sphere. It's noticeably flattened at the poles and swollen around the middle, like pizza dough spun in the air by a chef. If you measured from pole to pole through Jupiter's center, you'd get a shorter distance than if you measured across its equator. The difference is about 9,000 miles. Not insignificant when you're dealing with something already so vast. This spin also drives Jupiter's incredible weather patterns. Those bands of color you see in photographs, the white zones and brownish belts that stripe the planet from pole to pole, are actually jet streams, rivers of atmosphere flowing in opposite directions at different latitudes. The rapid rotation creates what's called the Coriolis effect, the same phenomenon that makes hurricanes spin on Earth. But on Jupiter, with its faster spin and lack of solid ground to create friction, these jet streams become permanent features, stable rivers of wind that have flowed in the same channels for as long as we've been watching. As you drift off tonight, imagine Jupiter spinning beneath you, clouds racing past at hundreds of miles per hour, sunrise and sunset flickering by like a time-lapse film. Time on Jupiter is compressed, urgent, relentless, and yet the planet itself has existed in this state for billions of years. What seems frantic from our perspective is, for Jupiter, simply the normal rhythm of existence. Long before telescopes, before spacecraft, before we understood that planets were worlds rather than wandering stars, humans looked up at Jupiter and wondered. The ancient Babylonians, living in Mesopotamia nearly 3,000 years ago, watched the night sky with remarkable dedication. They noticed that most stars remained fixed in their patterns, constellations that turned slowly through the seasons, but never changed their relationships to one another. But a few lights moved. These wanderers, the word planet, comes from the Greek word for wanderer, traced paths through the zodiac, and the Babylonians tracked them meticulously. They called Jupiter the star of Marduk, after their chief god, the deity who created order from chaos. This wasn't arbitrary mythology. There was something about Jupiter's steady, bright presence that suggested power and sovereignty. Unlike Mars, which seemed angry and red, or Mercury, which darted close to the sun and disappeared, Jupiter moved with dignified slowness, dominating the night sky whenever it was visible. But here's what's truly remarkable. The Babylonians didn't just watch Jupiter's movement, they predicted it. They developed mathematical techniques to calculate where Jupiter would appear in the sky months or even years in advance. Clay tablets covered in cuneiform script show geometric calculations that anticipate techniques we wouldn't formalize in Europe until over 1,000 years later. They were doing a form of calculus, tracking velocity and position, understanding that Jupiter's motion followed patterns that could be described mathematically. These ancient astronomers couldn't have known that Jupiter was a world, that it had moons, that storms larger than Earth churned in its atmosphere. They couldn't have imagined that one day humans would send machines to fly past it, to orbit it, to plunge probes into its clouds. But they knew it was important. They knew it was worth watching. And in a sense, they were right. Jupiter, as we'll discover throughout this journey, shapes our solar system in profound ways. The Babylonians sensed its significance even if they couldn't articulate why. Sometimes intuition precedes understanding by millennia. On a cold January night in 1610, an Italian mathematician and astronomer named Galileo Galilei pointed a newly improved telescope at Jupiter. What he saw changed everything. At first he noticed 3 small stars near Jupiter, arranged in a straight line. Curious, he sketched what he saw and continued observing over the following nights. The stars moved, not just drifting slowly like the background stars, but changing positions relative to Jupiter. Sometimes 3 were visible, sometimes 4. They appeared on one side of the planet, then the other. And then Galileo understood. These weren't stars at all. They were moons, orbiting Jupiter. This observation was revolutionary, almost dangerous. At the time, the prevailing belief, enforced by religious authority, was that Earth sat at the center of the universe, with everything else revolving around it. The sun, the moon, the planets, the stars, all supposedly circled Earth. But here were 4 objects clearly orbiting Jupiter, not Earth. The universe, it seemed, had multiple centers. If moons could orbit Jupiter, then perhaps Earth wasn't the cosmic hub after all. Perhaps Copernicus had been right when he suggested that Earth orbited the sun. Galileo named these moons the Medicean stars, after his patrons, though today we call them the Galilean moons, Io, Europa, Ganymede, and Callisto. These 4 worlds, and they are worlds, each with its own character and mysteries, would have been planets in their own right if they orbited the sun directly. Instead, they circled Jupiter in a celestial dance that has continued for billions of years. This discovery represents a threshold moment in human thought. Before Galileo's telescope, we imagined ourselves at the center of everything. After we began the long, humbling process of realizing our place in a much larger cosmos. Jupiter's moons were the first step in that journey. As you drift towards sleep, consider this. Every time we learn something new about the universe, we become simultaneously smaller and more connected to something vast. Galileo's moons whispered a truth that we're still absorbing 4 centuries later. We are not the center, but we are part of something extraordinary. Names matter. They shape how we think about things, how we relate to them. When ancient Romans looked up at the brightest wandering star in the night sky, outshone only by Venus and the moon, they named it after Jupiter, their king of gods, the ruler of sky and thunder, the deity who brought order and justice to both gods and mortals. It's a fitting name for a world that dominates our solar system with such overwhelming presence. And it's not just the Romans who associated this planet with royalty and power. The ancient Greeks called it Zeus, their own king of gods. The Babylonians named it after Marduk, their supreme deity. In ancient China, it was called Muxing, Muqiang, the wood star, associated with growth and expansion. In Hindu astronomy, it's Brihaspati, the guru of the gods, associated with wisdom and knowledge. Across cultures separated by thousands of miles and centuries of time, humans independently looked at this bright point of light and thought, this is something important, something powerful, something that deserves a name suggesting authority and magnitude. They were right in ways they couldn't have imagined. Jupiter doesn't just appear dominant in our sky. It actually dominates the solar system through sheer gravitational influence. Its mass shapes the orbits of asteroids and comets. It affects the paths of the other planets, including Earth. Some scientists believe Jupiter acts as a shield, its gravity deflecting dangerous comets away from the inner solar system, possibly making Earth a safer place for life to evolve. Whether Jupiter is truly our protector or sometimes our threat remains debated, but either way, its influence is undeniable. So tonight, as you journey through these facts, remember that you're exploring a world that humans have recognized as special for as long as we've been looking up. The name Jupiter carries weight. Not just linguistic weight, but the weight of thousands of years of humans gazing upward and sensing that this particular light in the sky was somehow significant, somehow royal, somehow deserving of our attention and wonder. Time is relative, not just in Einstein's physics, but in a more intuitive sense when you compare worlds. On Jupiter, the relationship between days and years becomes almost absurd. A day, one full rotation of the planet, happens so quickly that you'd barely have time to adjust to morning before evening arrived. But a year, one complete orbit around the sun, takes so long that a child born on Jupiter wouldn't celebrate their first birthday until they were nearly 12 years old by Earth's calendar. Let's sit with those numbers for a moment. In one Jovian year, Jupiter experiences more than 10,000 sunrises and sunsets. 10,000 days compressed into what we would call one trip around the sun. If you were somehow keeping time on Jupiter, you'd need a calendar wildly different from Earth's. Months would be meaningless. Weeks would be arbitrary. The sun would rise and set so frequently that the concept of day and night would feel less like fundamental divisions of time and more like the rapid flickering of light and shadow. And yet, from Jupiter's perspective, Earth must seem almost frantic. We spin more slowly, taking 24 hours for each rotation, but we whip around the sun in just 365 days. By the time Jupiter completes one leisurely orbit, Earth has circled the sun 12 times. Seasons on Jupiter last about 3 Earth years each, though the seasons are subtle, since Jupiter's axis is tilted only 3 degrees. Still, imagine a spring that lasts longer than most presidential terms, a winter that spans the time from one Olympics to the next. This is one of those facts that seems simple but opens into something deeper when you really contemplate it. Time isn't universal, it's local, particular to where you are and how you move through space. Jupiter experiences time differently than we do. Its days are brief, its years are long, and somewhere in the middle of those opposing rhythms, the planet simply exists, spinning and orbiting, indifferent to our human measurements and definitions. As you fall asleep tonight, let that thought settle. Time is flexible, negotiable, dependent on perspective. Even something as seemingly absolute as a day or a year changes when you travel far enough from home. Here's a paradox. Jupiter contains more mass than 318 Earths combined. Yet it's so spread out, so diffuse, that parts of it are less substantial than you might imagine. The upper atmosphere, where the pressure is similar to Earth's atmosphere at sea level, is so thin that if you were somehow protected from the cold and radiation, you could theoretically move through it by swimming motions. Not that there's anything to swim through exactly, it's gas, not water. But the density is so low that movement would feel more like floating through increasingly thick fog than plunging into an ocean. This tells us something crucial about Jupiter. There's no surface. On Earth, you can point to where the atmosphere ends and the ground begins. There's a definite boundary. But on Jupiter, the atmosphere just gets gradually denser as you descend. There's no moment where you'd suddenly splash down or touch solid ground. Instead, you'd sink deeper and deeper, the gas becoming thicker, the pressure increasing, the temperature rising, until eventually the gas becomes so compressed that it transitions into liquid. And even that transition happens gradually, without a clear boundary. Imagine falling through Jupiter. At first, you'd drift through thin clouds of ammonia ice, temperatures far below zero. As you sink, the atmosphere thickens, the pressure builds, the temperature climbs. Eventually, you'd reach a depth where the air around you is so dense that it's more accurate to call it a fluid. Keep descending, and the pressure becomes crushing. The temperature soars to thousands of degrees, and the hydrogen around you transforms into something exotic, a metallic liquid that doesn't exist naturally anywhere on Earth. And somewhere in the middle of all this, you'd lose consciousness, be crushed, be vaporized. There's no peaceful descent through Jupiter. It's a world without mercy for anything fragile. But still, that upper atmosphere, those thin, cold clouds where the journey would begin, remains strangely approachable. Parts of Jupiter are almost as insubstantial as a dream. It's only as you go deeper that the dream becomes a nightmare of pressure and heat. As you drift off to sleep tonight, you're doing something Jupiter's upper atmosphere does constantly. Existing in a state between solid and nothing, between substance and vapor, neither fully present nor fully absent. Distance in space becomes difficult to grasp after a certain point. We can understand a mile or 100 miles or even thousands of miles. But 484 million miles? That number is too large to feel real. So let's think about it differently. Think about light. Light is the fastest thing in the universe. Nothing can move quicker. A beam of light could circle Earth's equator more than 7 times in a single second. When you flip a light switch, the room illuminates essentially instantaneously. When you look at the moon, you're seeing it as it was 1.3 seconds ago. That's how long it takes light to travel from the moon to your eyes. The sun is farther away, so sunlight takes about 8 minutes to reach Earth. If the sun suddenly vanished, we wouldn't know for 8 minutes. We'd continue seeing sunlight, feeling its warmth, completely unaware that the source had disappeared. Now extend that outward to Jupiter. Sunlight takes 43 minutes to reach it. Think about what that means. When you see Jupiter in the night sky, the light reflecting off it left the planet over an hour ago. You're looking at Jupiter as it was in the past. Not the distant past, not years or centuries ago, but far enough back that entire conversations could have happened, meals could have been eaten, shows could have been watched in the time since that light began its journey. From Jupiter, the sun appears only about 1/5 as bright as it does from Earth. Not dark exactly, but significantly dimmer. Noon on Jupiter would feel like a perpetually overcast day on Earth, and yet Jupiter remains one of the brightest objects in our night sky, third only to the Moon and Venus. That's partly because of its size. There's a lot of surface area to reflect light, but also because of its thick cloud layer, which is surprisingly reflective. Distance creates a kind of loneliness. Jupiter exists in a colder, dimmer region of the solar system than we do. It receives less solar energy, less light, less warmth, and yet it's not cold in the way we might expect, because Jupiter generates its own heat, radiating more energy into space than it receives from the sun. But we'll get to that mystery soon. For now, just sit with this idea. Jupiter is far away. So far that light, the fastest messenger in the universe, takes the better part of an hour to travel between there and here. Here's something that puzzled astronomers for decades. When they measured the temperature of Jupiter's atmosphere and calculated how much heat it should be receiving from the sun, the numbers didn't match. Jupiter is warmer than it should be. Not dramatically warmer. It's still an incredibly cold world by human standards, but measurably, significantly warmer than solar heating alone can explain. Jupiter radiates about 1.6 times as much energy into space as it absorbs from the sun. That extra heat has to come from somewhere. The answer lies in Jupiter's past and its ongoing transformation. When Jupiter first formed 4.5 billion years ago, it was much hotter. The process of accretion, countless impacts of rocks, ice, and gas falling together under gravity, released tremendous energy. That primordial heat is still there, trapped inside the planet's enormous mass, but Jupiter is also slowly contracting, very slowly. Over millions of years, Jupiter's gravity pulls the planet inward, compressing it ever so slightly. This compression releases heat, the same way pumping up a bicycle tire makes the pump warm. So Jupiter is essentially still cooling down from its formation, but the process is so gradual that it will continue for billions of years more. The planet is losing heat at a pace we can barely measure, shrinking at a rate of perhaps a few centimeters per year, imperceptible on human timescales, but cumulatively significant over geological ages. This internal heat has profound effects. It drives some of Jupiter's weather patterns, creating convection currents where warm gas rises and cool gas sinks. It means Jupiter's atmosphere is more dynamic than it would be if the planet were heated only by distant sunlight. And it hints at what lies deep below the clouds, an interior that's hot, pressurized, and actively churning, even billions of years after the planet's birth. As you drift toward sleep, warmed by your blankets, consider that Jupiter too is warm, but from within. Not from fire or fusion, but from the slow, patient release of ancient heat, from the gradual contraction of a giant that will continue shrinking, cooling, and radiating for epochs beyond human imagination. Imagine standing somewhere on Jupiter, though of course you can't. There's no ground to stand on. But imagine floating above its clouds, looking toward the sun. The same sun that feels warm on your face during an Earth afternoon, the same sun that makes you squint when you forget your sunglasses, would appear smaller, dimmer, less commanding. From Jupiter's distance, the sun shrinks to about 1/5 its brightness. It would still be by far the brightest object in the sky, still clearly the sun, but it would cast a weaker light, a more tentative warmth. This diminished sunlight means Jupiter exists in what we might call perpetual twilight by Earth standards. High noon on Jupiter, with the sun directly overhead, would feel like Earth during that soft hour before sunset, when shadows lengthen and the light takes on a gentler quality. Not dark enough to need artificial light, but subdued, muted, as if the universe has turned down a cosmic dimmer switch. And yet, paradoxically, Jupiter itself shines brilliantly when we look at it from Earth. It's the third brightest natural object in our night sky, outshone only by the Moon and Venus. How can a world receiving so much less sunlight appear so bright to us? The answer lies in Jupiter's size and its clouds. There's simply so much surface area reflecting light back toward us. More than 120 Earths could fit across Jupiter's disk. And those clouds, made of ammonia, ice crystals, and other compounds, are remarkably reflective. They bounce back a high percentage of the sunlight that does reach them. So Jupiter exists in a strange duality. From its own perspective, it dwells in dimmer light, farther from the sun's warmth. But from our perspective here on Earth, it's a beacon in the darkness, one of the first stars to appear after sunset, often visible throughout the entire night. It's a reminder that brightness is relative, that how we perceive something depends entirely on where we're standing. The same object can be both dim and brilliant, depending on your point of view. As you close your eyes tonight, consider how perspective shapes everything, not just in astronomy, but in all of life. What seems faint from one angle glows from another. We tend to think of the sun as fixed, stationary, the anchor point around which everything else revolves. But that's not quite accurate. When planets orbit the sun, they don't really orbit around a perfect central point. Instead, both the planet and the sun orbit around their common center of mass, a point called the barycenter. For small planets like Earth, this barycenter lies so deep inside the sun that the wobble is negligible. But Jupiter is different. Jupiter is so massive that the barycenter between it and the sun actually lies just outside the sun's surface. What this means is that as Jupiter orbits, the sun orbits too, in a small circle. The sun wobbles. Not dramatically, the motion is subtle, a gentle swaying as the giant planet pulls it around, but measurably. If an alien astronomer were observing our solar system from another star, they might detect this wobble in the sun's motion, and deduce that a large planet must be orbiting it. In fact, this is exactly how we've discovered thousands of planets around other stars. We watch distant stars for tiny wobbles, periodic shifts in their motion or their light, and from those wobbles we can infer the presence of unseen planets. Jupiter, then, is massive enough to move the Sun. Think about that for a moment. The Sun contains 99.86% of all the mass in our solar system. It's so enormous that 1,000,000 Earths could fit inside it. And yet Jupiter, just one planet, is hefty enough to make this titanic ball of fusion wobble slightly as it passes by every 12 years. This gravitational influence extends beyond just the Sun. Jupiter affects the orbits of asteroids, comets, and even other planets. Its gravity reaches across millions of miles, tugging and pulling, reshaping trajectories, creating regions of stability and instability throughout the solar system. Jupiter is a sculptor of orbits, a gravitational artist working on a canvas millions of miles wide. And all of this happens silently, invisibly, patiently. Gravity doesn't announce itself. It simply pulls, constantly and inevitably, bending space and time around it. As you lie there, Earth's gravity is pulling you gently downward into your mattress, holding you safe. And far above, Jupiter's gravity is pulling the Sun, pulling asteroids, pulling its moons, exerting influence across distances that dwarf human comprehension. Here's something that seems impossible. Jupiter, the giant of our solar system, is less dense than oak, less dense than maple. If you could somehow carve a block of Jupiter and a block of many common woods, weigh them on a cosmic scale, the wood would be heavier for the same volume. Jupiter's average density is only about 1.33 grams per cubic centimeter, while Earth's is 5.51. Jupiter is puffy, inflated, held together more by gravity's grip than by the intrinsic closeness of its particles. This low density tells us, once again, that Jupiter is fundamentally different from rocky planets like Earth. Earth is made of heavy elements: iron, nickel, silicon, oxygen. These atoms pack tightly together, creating solid rock and metal. But Jupiter is mostly hydrogen, the lightest element in the universe, just one proton and one electron per atom. Even compressed by Jupiter's enormous gravity, hydrogen remains relatively light. It's only in the deepest interior, where pressures become extreme, that hydrogen is squeezed into more exotic, denser forms. Now, if we could theoretically place Jupiter in an enormous ocean, an ocean large enough to hold a planet, would it float like Saturn supposedly would? Probably not. Saturn's density is even lower, about 0.687 grams per cubic centimeter, less than water's 1.0, which gives rise to the often repeated claim that Saturn would float. Jupiter, being slightly denser than water, would sink, but it's a close thing. A planet with 318 times Earth's mass, sinking slowly through an imaginary cosmic ocean because it's just slightly denser than water. The image is absurd, impossible, and yet mathematically accurate. This low density also means that most of Jupiter is empty space in a sense. Even the solid parts of atoms, the nuclei and electrons, are mostly empty space when you zoom in far enough. Jupiter takes this to an extreme. It's a cloud of particles held together by gravity, vast distances between each atom compared to the size of the atoms themselves. If you could turn off Jupiter's gravity, the planet would dissipate into space, expanding outward until it became an imperceptibly thin cloud, stretching across millions of miles. Gravity is the only thing keeping Jupiter coherent. The invisible hand, squeezing all that lightness into a sphere. As you drift off, feel gravity holding you down, giving you weight, giving you substance. Without it, you too would be nothing. More than dispersed atoms, a cloud with no shape. Speed is another thing that changes with distance. Earth races around the sun at about 67,000 miles per hour. That's 18 miles every single second. If you could somehow stand still in space and watch Earth zip past, it would be a blur. But Jupiter, despite being so much more massive, moves more slowly through its orbit. It travels at a more relaxed 29,000 miles per hour, still phenomenally fast by human standards, but less than half Earth's orbital speed. This isn't because Jupiter is lazy or unmotivated. It's a consequence of orbital mechanics. The farther you are from the Sun, the more slowly you need to move to maintain a stable orbit. If Earth suddenly slowed to Jupiter's speed, we'd fall inward toward the Sun. If Jupiter suddenly accelerated to Earth's speed, it would be flung outward, possibly escaping the solar system entirely. Each planet moves at precisely the speed required to balance the Sun's gravitational pull, with its own tendency to move in a straight line. This balance, this delicate orbital dance, has been maintained for billions of years. There's something almost meditative about Jupiter's pace. While inner planets like Mercury whip around the Sun in mere weeks or months, Jupiter takes its time, 12 Earth years for a single orbit. No rushing, no hurry, just a steady, patient progression through the zodiac constellations. Ancient astronomers noticed this stately pace and used it to mark time. Jupiter became a cosmic clock, its position among the stars serving as a calendar for long-term cycles and events. From Jupiter's perspective, if we could imagine the planet having a perspective, Earth must seem frantic. We orbit the Sun 12 times in the span it takes Jupiter to go around once. We experience 12 summers, 12 winters, 12 springs, 12 autumns, while Jupiter barely completes a single circuit. Time, once again, is relative. What seems like a reasonable pace from one viewpoint appears either sluggish or hectic from another. As you lie in bed, you're moving at 67,000 miles per hour right now, orbiting the Sun along with Earth. You don't feel it because you're moving with the planet, but it's happening. And far beyond, Jupiter continues its slower journey, covering vast distances but taking its time, proving that even in the cosmos, there's no single correct speed. Everything moves as fast or as slow as it needs to, and the universe accommodates all paces. Different cultures looked at Jupiter and saw different meanings, different patterns, different relationships to human time. In ancient China, astronomers noticed that Jupiter took approximately 12 years to complete one orbit around the Sun, one journey through the background stars. This 12-year cycle resonated deeply with the Chinese zodiac, which also operates on a 12-year pattern. Each year was associated with an animal: rat, ox, tiger, rabbit, dragon, snake, horse, goat, monkey, rooster, dog, and pig, and these animals cycled in the same rhythm as Jupiter's orbit. They called Jupiter Sui Xing, the year star, not just because it marked the years, but because its position in the sky could tell you which year of the cycle you were in. If you knew where Jupiter was among the constellations, you could determine what year it was in the 12-year cycle. The planet became a celestial calendar, a clock in the sky that tracked time on scales longer than a single human year, but shorter than a lifetime. This is a beautiful example of humans finding patterns in the cosmos and weaving those patterns into culture and daily life. The Chinese didn't know what Jupiter was. They didn't know it was a giant planet made of hydrogen, didn't know about its moons or its storms. But they knew it was regular, predictable, trustworthy. You could count on Jupiter. Every 12 years, it returned to the same position, starting the cycle again. And they were right to trust it. Jupiter's orbit is remarkably stable. It's been following essentially the same path for billions of years, and it will continue for billions more. Empires rise and fall, languages evolve and disappear, entire civilizations emerge and crumble into dust. But Jupiter keeps circling the sun at the same steady pace, indifferent to the dramas unfolding on the tiny blue world below. As you close your eyes, think about cycles, the rhythms that structure our lives, days and nights, weeks and months, the seasons turning, birthdays marking another trip around the sun, and beyond our small cycles, larger ones, Jupiter's 12-year orbit, Saturn's 30-year journey, the slow precession of Earth's axis, taking 26,000 years. The universe operates in nested cycles, rhythms within rhythms, patterns that range from the frantic to the glacial. We exist somewhere in the middle, aware of the cosmic clockwork, watching the year star mark time in the eternal sky. Now we come to one of Jupiter's most famous features, perhaps the most iconic storm in the entire solar system, the Great Red Spot. When you see images of Jupiter, this is often what draws the eye. A massive oval, rust-colored or salmon pink, depending on the observation, swirling in the planet's southern hemisphere. It's a storm, not just any storm, but an anticyclone, a high-pressure system rotating counterclockwise, large enough to swallow Earth whole with room to spare. And it's old. Astronomers first definitively recorded the Great Red Spot in 1831, giving it a confirmed age of at least 190 years. But there are earlier observations that might be the same storm. In 1665, Italian astronomer Giovanni Cassini described a similar feature he called the permanent spot. If that was the Great Red Spot, then this storm has been churning for over 350 years. 3.5 centuries of continuous existence. Think about what was happening on Earth when this storm may have begun. The middle of the scientific revolution, long before. Industrialization, before electricity, before flight, before computers. And through all of that human history, the Great Red Spot has simply persisted, spinning, enduring. How can a storm last so long? On Earth, hurricanes last days or weeks at most. They form over warm ocean water, draw energy from that warmth, and then dissipate when they make landfall and encounter the friction of solid ground. But Jupiter has no land. There's nothing to slow the storm down, no ground to sap its energy. And Jupiter's internal heat, combined with the planet's rapid rotation, keeps pumping energy into the atmosphere. The Great Red Spot feeds on this energy, sustaining itself year after year, decade after decade, century after century. But nothing lasts forever, even on Jupiter. The Great Red Spot is shrinking. Observations show it's less than half the size it was in the 1800s. A century and a half ago, you could fit 3 Earths inside it. Now perhaps 1.5. Why is it shrinking? No one knows for certain. Maybe the dynamics that created it are shifting. Maybe it's merging with other storms, losing mass. Maybe it's simply dying, and we're witnessing the slow decline of a storm that has existed longer than any human institution. As you drift towards sleep, imagine that storm spinning silently in space, older than any government on Earth, older than the United States, older than most countries. A tempest that has outlived empires, witnessed from afar the entire course of modern history, indifferent and eternal, or at least nearly eternal. The great red spot doesn't just sit there, a static mark on Jupiter's face. It spins. The entire storm rotates counterclockwise, taking about 6 Earth days to complete one full turn. That might seem slow, 6 days for a single rotation, but remember, this isn't a small weather pattern. The storm is wider than Earth. If you were somehow riding along with the edge of the storm, you'd be traveling at about 270 miles per hour, faster than any hurricane wind speed ever recorded on Earth. 270 miles per hour. That's roughly 4.5 miles per minute. A speed where atmosphere becomes a weapon, where anything loose becomes a projectile, where structures crumble and landscapes reshape. And that's the speed at the storm's outer edge. We don't know precisely what's happening in the center, in the eye of this vast anticyclone. Is it calmer there, like the eye of an Earth hurricane? Or does the whole system maintain its violence all the way through? The counterclockwise rotation tells us this is a high-pressure system, an anticyclone. On Earth, high pressure usually means calm weather, clear skies, gentle winds. But on Jupiter, high pressure creates one of the most violent, enduring storms we've ever observed. The rules are different there. Pressure and temperature behave in unexpected ways. The atmosphere is so deep, so massive, that weather systems can grow to planetary scales and maintain their structure for centuries. Watching the great red spot through a telescope is like watching a clock with only one hand, moving so slowly that you need to observe it over days to see the change. But that slow rotation represents enormous energy. The storm contains more kinetic energy than all of Earth's weather systems combined. All the hurricanes and typhoons and thunderstorms happening right now across our entire planet. And it releases this energy gradually, a slow burn rather than a quick explosion, which is part of why it lasts so long. Close your eyes and try to imagine something spinning for 6 days straight. Most things we encounter spin quickly: tops, wheels, drills, fans. But the great red spot rotates with the patience of geological time, the pace of continental drift, the slow turn of seasons. It's a different kind of motion, one that operates on scales more suited to planets than to human experience. Why is the great red spot red? It's a question that seems simple but opens into complicated chemistry and atmospheric science. The short answer is, we're not entirely sure. The longer answer involves photochemistry, the way sunlight interacts with molecules in Jupiter's atmosphere, breaking them apart and allowing them to recombine into new compounds. Jupiter's atmosphere contains simple molecules: hydrogen, helium, methane, ammonia, water vapor. But when ultraviolet light from the sun strikes these molecules, it can break their chemical bonds, creating fragments, what chemists call free radicals. These fragments are reactive, eager to bond with other atoms and molecules. In the upper layers of Jupiter's atmosphere, this constant breaking and reforming of chemical bonds creates a variety of complex organic compounds. Long chains of carbon and hydrogen, sulfur compounds, phosphorus compounds, perhaps even more exotic chemicals we haven't identified yet. Some of these compounds are colored. Sulfur, for instance, can appear red or orange under certain conditions. phosphorus compounds can also produce reddish hues. The leading theory is that the great red spot's color comes from these photochemical products being churned up from deeper in the atmosphere, where they're created, and exposed to more sunlight at the storm's upper levels. The storm acts like a giant mixer, bringing deep material to the surface where it can be illuminated and colored by ongoing chemical reactions. But here's the mystery. The great red spot isn't always the same shade of red. Sometimes it appears brick red, deep and vivid. Other times it fades to a pale salmon or even brownish orange. These color changes might reflect variations in the chemical composition, changes in the altitude of the storm's clouds, or shifts in how much material is being dredged up from below. The storm is literally changing its appearance over time, like a mood ring for Jupiter, reflecting internal processes we're only beginning to understand. This uncertainty, this not quite knowing, is one of the beautiful things about science. We can observe the great red spot, measure its size and speed, track its evolution, but the simple question, why is it red, remains partially unanswered. Nature keeps some secrets, even when we're looking right at them. As you drift off, let that be a comfort. Not everything needs to be fully explained or understood to be appreciated. Sometimes mystery is its own kind of knowledge. Nothing in the universe is truly permanent, not even storms that have raged for centuries. The great red spot is shrinking. In the late 1800s, when astronomers began making detailed measurements, the storm was about 25,000 miles across at its widest point, large enough to fit 3 Earths side by side. By the 1980s, it had shrunk to about 2 Earths wide. Today, it's roughly 10,000 miles across, big enough for maybe 1¼ Earths. The change is dramatic, undeniable, and ongoing. No one knows exactly why the storm is shrinking, though theories abound. Perhaps the dynamics of Jupiter's atmosphere are shifting in ways that starve the storm of energy. Perhaps smaller storms that once merged with the great red spot, feeding it new material, are now being deflected or absorbed by other systems. Perhaps the planet's climate, if we can use that word for a gas giant, is changing in subtle ways that make maintaining such a large storm more difficult. What's particularly interesting is that while the storm is shrinking horizontally, it may be growing vertically, stretching higher into Jupiter's atmosphere. And as it shrinks, it appears to be spinning faster, like a figure skater pulling in their arms to accelerate a spin. The storm is transforming, changing its shape and character even as it diminishes in size. Will the great red spot disappear entirely? Maybe. Probably, eventually. Some scientists think it might dissipate within the next few decades. Others believe it could stabilize at a smaller size and persist for centuries more. We're witnesses to something rare, the potential death of a storm that has outlived multiple human generations. A weather system that was already ancient when Charles Darwin was developing his theory of evolution. There's something melancholy about this. Humans have been watching the great red spot for nearly 2 centuries of dedicated observation, and possibly much longer. It's become iconic, a symbol of Jupiter, one of the most recognizable features in the entire solar system. The idea that it might not be there for future generations feels like a loss, even though we have no personal connection to a storm on a distant planet. But that's part of being human. We form attachments even to things we've never touched. to phenomena millions of miles away, to storms we'll never feel. As you close your eyes tonight, the great red spot continues spinning, shrinking imperceptibly with each rotation, heading toward an uncertain future. Like all of us, it exists in time, subject to change, impermanent, despite its apparent endurance. And perhaps that makes it more precious, not less. Beautiful because it won't last forever. Significant because we're alive to witness it while it's still here. The great red spot might be the most famous, but it's far from alone. Jupiter's atmosphere is constantly churning with storms, dozens of major systems at any given moment, plus countless smaller disturbances. Look at any detailed image of Jupiter and you'll see white ovals, brown patches, smaller red storms, swirls and eddies scattered across the planet's face like cream stirred imperfectly into coffee. These smaller storms can still be enormous by Earth standards. A small storm on Jupiter might be larger than the largest hurricane Earth has ever produced. White ovals are high-pressure systems like the Great Red Spot, but without the red coloration, perhaps because they don't reach as deep into the atmosphere, or because the chemistry at their altitude produces different compounds. Brown regions, often called barges or brown ovals, might be areas where we're seeing deeper into the atmosphere through gaps in the upper cloud layers. What's fascinating is that these storms interact with each other. They can merge, two storms spiraling together and combining into a single, larger system. This happened in 2000 when three white ovals that had existed for 6 decades merged together. The resulting storm eventually turned red and earned the nickname Red Spot Jr., or Oval BA. For a while, Jupiter had 2 prominent red storms, and astronomers wondered if Red Spot Jr. might eventually rival or even replace the Great Red Spot. So far, that hasn't happened. Red Spot Jr. is smaller and less stable, but the possibility remains. Storms can also tear each other apart, competing for the same energy and atmospheric resources. Strong jet streams can shear a storm, stretching it until it disintegrates, and new storms form constantly, born from the turbulence where wind belts moving in opposite directions meet and shear against each other. Jupiter's atmosphere is a battleground, a dynamic system where order and chaos compete constantly. The banded structure, those stripes of different colors running parallel to the equator, represents a kind of order, stable patterns maintained by the planet's rapid rotation. But within and between those bands, chaos reigns, storms forming, evolving, merging, dissipating, an ever-changing tapestry of weather that never reaches a final, stable state. As you drift towards sleep, imagine that planet spinning in the darkness, its atmosphere alive with motion, dozens of storms larger than terrestrial hurricanes swirling simultaneously, the whole thing choreographed by gravity, heat, and rotation into a dance that's been ongoing for billions of years and will continue long after humans are gone. Lightning exists on Jupiter. This might seem surprising. Lightning feels like such an Earth phenomenon, associated with thunderstorms and summer afternoons. But the physics of lightning are fairly universal. Whenever you have charge separation in an atmosphere, whenever positive and negative charges build up in different regions, eventually the electrical potential becomes strong enough that current jumps across the gap in a brilliant flash. Jupiter's lightning is different from Earth's, though. For one thing, it's more powerful. The strongest lightning bolts on Jupiter release about 3 times as much energy as the most powerful bolts ever detected on Earth. These are not gentle sparks. They're massive electrical discharges that would, if they occurred in Earth's atmosphere, be utterly devastating. NASA's Juno spacecraft has been studying Jupiter's lightning in detail, and it discovered something unexpected. Most of Jupiter's lightning occurs near the poles, not at the equator. This is backwards from Earth, where tropical regions produce far more lightning than polar regions. Why? It might have to do with Jupiter's internal heat. The poles might have more convection, more churning of the atmosphere that creates the conditions for charge separation. Juno also detected lightning deep within Jupiter's atmosphere, far below the visible cloud tops. These deep lightning bolts occur in water clouds. Yes, Jupiter has water, though it exists mostly as ice crystals and vapor deep in the atmosphere, where pressures and temperatures are different from the surface we see. The presence of water lightning tells us something important. Water is more abundant on Jupiter than we previously thought, though it's hidden beneath layers of ammonia clouds. Imagine what it would be like to witness Jovian lightning, brilliant flashes illuminating vast cloudscapes, electrical discharges powerful enough to vaporize anything in their path, occurring thousands of miles below where we could ever safely observe them. Jupiter's storms aren't just wind. They're electrical generators, cosmic capacitors, discharging their accumulated energy in bursts of light and heat that briefly rival the sun's surface temperature. On Earth, hurricanes die when they make landfall. The mechanism is straightforward. Hurricanes draw energy from warm ocean water. As long as they stay over the ocean, they can maintain or even increase their strength. But the moment they encounter land, they're cut off from their energy source. Friction from trees, buildings, hills, and mountains slows the winds. Without fuel and facing resistance, the storm weakens, usually dissipating within hours or days of reaching the coast. Jupiter has no coast. There's no land anywhere. The atmosphere just continues downward, getting denser and hotter, transitioning gradually from gas to liquid without any solid boundary. This means storms on Jupiter never encounter the friction that kills Earth's hurricanes. They can persist indefinitely, as long as the atmospheric conditions that created them remain stable. This is why the Great Red Spot can exist for centuries. It's why many of Jupiter's white ovals have been observed for decades. These storms are essentially self-sustaining, drawing energy from Jupiter's internal heat and the planet's rapid rotation, never encountering anything that would force them to dissipate. There's something almost alive about this. Jupiter's storms behave like organisms that never age, never die of natural causes. They can be destroyed, merged with other storms, torn apart by wind shear, but they don't simply run out of energy and fade. They persist until something actively ends them. This longevity means Jupiter's atmosphere has a kind of memory. Features we see today might be related to features that existed centuries ago. Storms can spawn child storms, which themselves might last for decades. The planet's weather isn't just a snapshot of current conditions. It's a palimpsest of atmospheric history, layers of patterns built up over vast timescales. As you fall asleep, storms rage in perpetual motion, enduring beyond human lifetimes. When we look at Jupiter, we see a flat disk, a two-dimensional image. But Jupiter's storms aren't flat. They extend vertically. towering structures that reach through multiple layers of atmosphere. The Great Red Spot, for instance, isn't just a surface feature. It's a column of churning atmosphere that extends perhaps hundreds of miles deep. On Earth, the tallest thunderstorms, the most intense supercells, can reach about 10 or 12 miles high, from ground level to the top of the cloud. That's already impressive, a tower of storm tall enough to pierce the stratosphere. But Jupiter's storms can be 10 times that height, or more. A single storm system could extend from sea level on Earth all the way to the edge of space, where the atmosphere thins into vacuum. This vertical structure exists because Jupiter's atmosphere is so deep. Earth's atmosphere is relatively thin. Most of the mass is concentrated in the lowest 10 miles. But Jupiter's atmosphere extends thousands of miles, with pressure and temperature increasing gradually as you descend. Different cloud layers form at different altitudes depending on temperature and what chemicals can condense there. The topmost clouds are ammonia ice, forming at the coldest temperatures high in the atmosphere. Below that, you'd encounter ammonium hydrosulfide clouds, a compound that doesn't exist naturally on Earth. Deeper still, there are water clouds, similar in composition to Earth's clouds, but existing under much greater pressure. Jupiter's storms can span all these layers, connecting the freezing upper atmosphere to the warmer, denser regions below. What happens in these vertical structures? We don't know precisely. Material likely circulates, rising in some areas and sinking in others, carrying heat and chemicals between layers. The storms might work like enormous engines, converting thermal energy into motion. As you drift off, picture these towering columns of storm, structures taller than mountains. Spanning atmospheric layers we've barely begun to understand. Jupiter's most obvious visual feature, beyond the Great Red Spot, is its stripes. Even in a small telescope, you can see light and dark bands running parallel to the equator, circling the entire planet. These aren't just decorative markings, they're jet streams, fast-moving rivers of atmosphere flowing at different latitudes, and crucially, they flow in opposite directions. The light bands, called zones, are regions where gas is rising from deeper in the atmosphere. As it rises, it cools and forms high-altitude clouds of ammonia ice, which are bright and reflective. The darker bands, called belts, are regions where gas is sinking back down. These descending flows carry material from higher up, where it's been chemically altered by sunlight, giving the belts their brownish color. Adjacent bands flow in opposite directions. One might flow eastward at 200 miles per hour, while its neighbor flows westward at a similar speed. Where these bands meet, where eastward and westward flows shear against each other, turbulence erupts. This is where storms form, born from the collision of opposing currents. This banded structure exists because of Jupiter's rapid rotation and something called the Coriolis effect, the same phenomenon that makes hurricanes spin on Earth. As Jupiter spins, it deflects moving air into east-west flows rather than north-south flows. The result is this pattern of alternating jets, stable structures that have persisted for as long as we've been observing Jupiter. What's remarkable is the stability. Earth's jet stream, the high-altitude wind that drives much of our weather, meanders and shifts position. But Jupiter's jets stay locked in place, decade after decade. The zones and belts might change shade slightly. Storms might form and dissipate along their boundaries. but the fundamental banded structure remains constant. It's weather that behaves almost like geology, patterns carved into the atmosphere that endure like continents. Sleep now, while Jupiter's winds race eastward and westward, unchanging rivers in an ocean of gas. Sometimes we get to witness change on Jupiter within a human lifetime, which is extraordinary given how slowly some processes occur there. In 2000, 3 white oval storms, features that astronomers had been tracking since the 1930s, came together and merged into a single, larger storm. These ovals had been roughly the same size for 6 decades, 3 separate systems spinning in Jupiter's southern hemisphere. But gravitational interactions, changes in the surrounding wind patterns, or perhaps just the chaotic dynamics of the atmosphere brought them together. When storms merge on Jupiter, they don't simply collide and dissipate. Instead, they combine with the resulting storms sometimes larger and more powerful than the originals. In this case, the merged storm created a new white oval, which astronomers began tracking carefully. Then something unexpected happened. The storm changed color. By 2006, the once white oval had developed a distinct reddish hue. It wasn't as intensely red as the Great Red Spot, but it was clearly no longer white. Scientists nicknamed it Red Spot Jr., or sometimes Oval BA in technical literature. For a time, Jupiter had 2 prominent red storms, and there was speculation that Red Spot Jr. might grow to rival or even replace the shrinking Great Red Spot. That hasn't happened. Red Spot Jr. has remained smaller and has fluctuated in intensity, but its existence proved that the Great Red Spot isn't entirely unique. Whatever process creates the red coloration can occur in other storms under the right conditions. Why did the storm turn red after merging? Perhaps the merged storm became powerful enough to reach deeper into Jupiter's atmosphere, dredging up material from below that contains the chemical precursors for red compounds. Or maybe the increased altitude of the storm's clouds exposed them to more intense sunlight, driving photochemical reactions that produce color. We're still working out the details, but the transformation demonstrated something important. Jupiter's appearance can change noticeably even within decades. The planet isn't static, it's evolving, dynamic, surprising us with changes we're privileged to witness. One of the strangest things about Jupiter is that it has no surface in any meaningful sense. On Earth, there's an obvious distinction. Above you is air, below you is ground. The transition is sharp, definite. You can point to where the atmosphere ends and the solid Earth begins. But on Jupiter, there's no such boundary. Instead, as you descend into Jupiter's atmosphere, the pressure simply increases. Gradually at first, the upper atmosphere is quite thin, similar to Earth's stratosphere. But as you go deeper, the gas gets denser. The pressure builds. Eventually, the atmosphere becomes so compressed that calling it gas feels inadequate. It's more like a fluid, but there's no moment where it suddenly becomes liquid. No splash, no surface tension, no clear phase transition. Just a continuous gradient from thin gas to thick gas to supercritical fluid, where the distinction between gas and liquid becomes meaningless. If you were descending through Jupiter in a magical, indestructible vessel that could withstand the pressure, you'd never know when you crossed from atmosphere to interior. The temperature would steadily increase, the pressure would build, the density would grow, but you'd never hit anything solid. you just keep sinking through gas that becomes fluid, that becomes something stranger still, until eventually the pressure and heat would crush and vaporize even your theoretical indestructible ship. Deep enough inside Jupiter, the hydrogen is compressed so intensely that it behaves like a liquid metal, conducting electricity. This metallic hydrogen exists nowhere naturally on Earth. It requires pressures millions of times greater than our atmosphere. And even deeper, there might be a core, a region of heavier elements like rock and ice, but it's probably not a distinct, solid sphere. More likely, it's dissolved or fuzzy, blending gradually into the metallic hydrogen above it. Jupiter challenges our categories. It's not quite a gas, not quite a liquid, not quite anything we have easy words for. It exists in states of matter that we can barely replicate in laboratories. As you drift towards sleep, softening into unconsciousness, you're enacting your own phase transition, dissolving the boundary between waking and dreaming, becoming something in between. Temperature on Jupiter spans an extraordinary range. At the cloud tops, the visible surface we see in photographs, the temperature hovers around 234 degrees Fahrenheit. That's colder than any temperature naturally occurring on Earth's surface. Cold enough to freeze carbon dioxide solid. Cold enough that exposed flesh would freeze instantly. But descend into the atmosphere and the temperature rises. The increase is steady, driven by Jupiter's internal heat and the crushing pressure. By the time you're a few hundred miles down, temperatures might be close to room temperature, a brief, strange zone where a thermometer would read numbers familiar to human experience. But keep going. The temperature continues climbing. 1,000 miles down, it might be several hundred degrees. 2,000 miles down, thousands of degrees. By the time you reach the region where hydrogen transitions to metallic form, temperatures are tens of thousands of degrees Fahrenheit, hotter than the surface of the sun. This enormous temperature gradient drives convection, the process where hot material rises and cool material sinks. Convection is what creates weather on Earth. Warm air rises, cools, then sinks, creating circulation patterns that drive winds and storms. On Jupiter, convection operates on a planetary scale, with currents rising and falling across thousands of miles, spanning temperature differences that would vaporize any material known to science. And yet, all of this heat is trapped inside. Jupiter's surface is frozen, an icy ceiling over a hellish interior. The planet is like an insulated oven, holding its primordial warmth inside, leaking it out slowly over billions of years. From the outside, Jupiter looks cold, serene, a pastel-colored world of gentle swirls. But that's deceptive. Beneath those pretty clouds lies heat intense enough to melt rock, to ionize matter, to create conditions more extreme than almost anywhere else in the solar system, except the sun itself. Beauty often conceals violence. Serenity can hide chaos. As you settle into sleep, warmth held close beneath your blankets. Consider Jupiter's warmth, trapped deep below its frozen face, radiating slowly into the void. Near Jupiter's poles, something strange happens. Instead of the orderly bands that stripe most of the planet, storms cluster together in complex, sometimes geometric patterns. NASA's Juno spacecraft, which orbits Jupiter in a path that takes it over the poles, has captured images of these clusters, arrangements of cyclones that form pentagons, hexagons, and other polygonal shapes. At Jupiter's north pole, there's a central cyclone surrounded by 8 other cyclones, arranged in an octagonal pattern. At the south pole, one central cyclone is surrounded by 5 others, forming a pentagon. These aren't random. The storms maintain their relative positions, locked together in gravitational and atmospheric interactions that create stable geometries. Why do these patterns form? It has to do with the mathematics of turbulence and rotation. When multiple storms interact, they influence each other through their wind fields. They can't get too close or they'll merge. They can't get too far apart or they lose their coordinated motion. The result is that they settle into configurations that represent stable equilibrium, geometric arrangements where each storm is held in place by its neighbors. Similar patterns occur in other physical systems. Beehive cells are hexagonal because that's the most efficient way to pack circles together. Crystals form geometric patterns because atoms arrange themselves in configurations that minimize energy. Jupiter's polar storms are following the same deep mathematical principles, finding shapes that represent balance in a chaotic system. There's something almost mystical about it. How chaos, given enough time and the right constraints, spontaneously generates order. How random turbulence can create geometry. The universe seems to prefer certain patterns, certain shapes, returning to them again and again across vastly different scales and systems. As you close your eyes, imagine those storms at Jupiter's poles, arranged like jewels in a crown, hexagons and pentagons spinning in the darkness, proof that even chaos has structure. Even turbulence has hidden rules that guide it toward beauty. Jupiter is simple, at least in terms of composition. Strip away all the complexity, the storms, the colors, the bands and zones, and you're left with mostly just 2 elements, hydrogen and helium. About 90% hydrogen, 10% helium, with everything else. Methane, ammonia, water, sulfur, phosphorus, complex organic molecules, making up less than 1% of the total mass. This composition is significant because it mirrors the composition of the Sun, and by extension, the primordial solar nebula, the cloud of gas and dust that collapsed to form our solar system 4.6 billion years ago. In the early solar system, hydrogen and helium were by far the most abundant elements, because they're the most abundant in the universe. They were created in the Big Bang and during the first generation of stars, while heavier elements like carbon, oxygen, and iron were forged later in stellar cores and supernova explosions. Jupiter formed from this primordial material, capturing and holding on to the lightest elements that Earth, being smaller and warmer, couldn't retain. Earth's atmosphere is mostly nitrogen and oxygen, heavier elements that Jupiter has too, but only in trace amounts. In a sense, Jupiter represents what the solar system was made of before planets like Earth differentiated, before heavy elements sank to form cores and light elements escaped to space. Those trace compounds, though small in quantity, are crucial. They're what create Jupiter's colors, its clouds, its weather. Ammonia forms white clouds. Methane absorbs red light, contributing to some of the blue tints. Complex organic molecules created by photochemistry give us browns and reds. Water, hidden deep in the atmosphere, forms clouds and drives convection. Jupiter is mostly hydrogen, but it's the tiny amounts of other stuff, the impurities, the spices, that give the planet its character. As you drift off, breathing air that's mostly nitrogen and oxygen, consider that you're made of trace elements too. carbon, phosphorus, iron, calcium, bits of stardust wrapped in water, animated by electrical signals. Jupiter and you are both composed of the universe's inventory, just in different proportions, different arrangements, same ingredients, different recipes. Why does Jupiter have so many colors? White zones, brown belts, red storms, blue-gray regions. The planet looks like an abstract painting, swirls of different hues blending and contrasting. The answer lies in chemistry and temperature gradients. Different compounds condense into clouds at different temperatures, which means they form at different altitudes in Jupiter's atmosphere. The coldest regions are at the top, where ammonia freezes into ice crystals. Ammonia ice is white, so regions with thick ammonia clouds appear bright and reflective. These are the white zones we see. Below the ammonia layer, temperatures are warmer, and different compounds can condense. Ammonium hydrosulfide, a molecule containing nitrogen, hydrogen, and sulfur, forms clouds with a brownish or reddish tint. Deeper still, water condenses into clouds, though we rarely see these directly because they're obscured by the layers above. The brown belts might be regions where we're seeing deeper into the atmosphere, through gaps or thin spots in the ammonia clouds, glimpsing the darker material below. Or they might contain photochemical products, organic molecules created when sunlight breaks apart methane and ammonia, allowing them to recombine into more complex colored compounds. The reds and oranges, particularly in storms like the Great Red Spot, likely come from these photochemical products being churned up from deeper levels and exposed to sunlight. Sulfur and phosphorus compounds can produce various shades of red, orange, and yellow. The exact recipes remain uncertain, but the general principle is clear. Jupiter's atmosphere is a laboratory where temperature, pressure, and sunlight drive constant chemical reactions, creating a palette of colors that shift and evolve over time. Jupiter's beauty is chemistry made visible. Every color tells a story about temperature, altitude, molecular composition, and the endless interactions between light and matter. As you close your eyes, let those colors fade, the swirls and bands dissolving into the darkness behind your eyelids. Chemistry giving way to dreams. The deeper you go into Jupiter, the stranger things become. We've established there's no solid surface, just gas becoming denser and denser. But at a certain depth, roughly 20,000 miles below the cloud tops, something remarkable happens. Hydrogen transforms into a form that doesn't exist naturally anywhere on Earth. Under normal conditions, hydrogen is a gas made of paired atoms, H2 molecules. It's an insulator, meaning it doesn't conduct electricity. But squeeze hydrogen hard enough, subject it to pressures millions of times stronger than Earth's atmosphere, and the molecular bonds break. The electrons that normally orbit individual atoms get stripped away, becoming free to move through the material. What you're left with is metallic hydrogen, a liquid that conducts electricity like copper or silver, except it's made entirely of the universe's simplest element. This metallic hydrogen ocean is crucial to understanding Jupiter. It's this electrically conductive fluid, swirling and churning as Jupiter rotates, that generates the planet's enormous magnetic field through a dynamo process. Moving conductive fluid creates electric currents, and those currents create magnetism. The faster the fluid moves and the more of it there is, the stronger the magnetic field. Jupiter has an abundance of both. a vast ocean of metallic hydrogen spinning rapidly as the planet completes its 10-hour rotation. We've never been able to create stable metallic hydrogen in laboratories on Earth. Scientists have managed to produce it momentarily under extreme pressures, but it exists only for fractions of a second before reverting to normal hydrogen. Yet on Jupiter, there's an entire ocean of it, a planetary-scale reservoir of exotic matter that's been continuously present for billions of years. Imagine that, an ocean made of metal that's also made of the lightest element, a liquid that conducts electricity but contains no actual metal atoms, existing under pressures that would instantly crush anything from Earth's surface. Jupiter's interior is as alien as any science fiction, a realm where familiar materials behave in unfamiliar ways, where the normal rules bend into something strange and wonderful. At the very center of Jupiter, beneath the metallic hydrogen ocean, beneath thousands of miles of compressed atmosphere, there should be a core. Traditional models of planet formation suggest Jupiter formed when a rocky core, perhaps 10 to 20 times Earth's mass, grew large enough that its gravity could capture the surrounding hydrogen and helium gas. The core came first, the atmosphere second. That's the theory anyway. But recent measurements from the Juno spacecraft suggest the reality might be more complicated. Juno's gravity measurements, incredibly precise readings of how Jupiter's mass is distributed, indicate that if there is a core, it's not a neat, solid sphere. Instead, it seems to be fuzzy, diffuse, possibly partially dissolved into the surrounding metallic hydrogen. Imagine trying to hold a sugar cube at the bottom of a glass of water, but the water is so hot and under so much pressure that the sugar starts dissolving, creating a gradient where there's no clear boundary between cube and liquid. Why would Jupiter's core dissolve? Perhaps during the planet's early history, when it was still hot from formation, a massive impact, another planet-sized body colliding with Jupiter, stirred up the interior, mixing core material with the metallic hydrogen. Or perhaps the extreme temperatures and pressures at Jupiter's center simply make it impossible for a distinct core to exist. At those conditions, rock and metal might become soluble in metallic hydrogen, the way salt dissolves in water. This fuzzy core challenges our understanding of how giant planets form and evolve. It suggests Jupiter's history might be more violent or chaotic than we imagined. And it reminds us that even solid concepts like a planetary core become ambiguous under extreme conditions. What does solid even mean when temperatures are 50,000 degrees and pressure is millions of atmospheres? Our everyday categories fail. Jupiter exists in a regime where matter behaves in ways that defy simple classification, where cores can be fuzzy and metals can be made of hydrogen. Sleep now, while Jupiter keeps its secrets, its heart hidden beneath layers of exotic matter we're only beginning to understand. 20,000 miles. That's the distance you'd need to descend into Jupiter before hydrogen transforms from a molecular gas into a metallic liquid. To put that in perspective, Earth's diameter is about 8,000 miles. You'd have to travel a distance equal to 2.5 Earths stacked end to end, all of it through increasingly dense atmosphere before reaching this exotic phase transition. The conditions at this boundary are extreme. Pressure is roughly 2 million times Earth's atmospheric pressure at sea level. Temperature is tens of thousands of degrees Fahrenheit. At these conditions, hydrogen molecules can no longer hold together. The pressure forces atoms so close that their electrons break free, creating a sea of positively charged hydrogen nuclei swimming in a fluid of electrons. The definition of a metal at the atomic level. This transition doesn't happen suddenly. There's probably a gradient zone where molecular hydrogen and metallic hydrogen coexist, mixing and transitioning over some depth range. But somewhere in that region, the character of the material fundamentally changes, from insulator to conductor, from transparent to opaque, from something we might recognize as gas to something entirely alien. Everything below this boundary, more than 90% of Jupiter's volume, is metallic hydrogen. It's the dominant form of matter inside the planet, an ocean deeper than any Earth ocean could ever be, stretching all the way down to the fuzzy core region. And it's constantly in motion, driven by Jupiter's rotation and internal heat, circulating in complex patterns we can only infer from observations of the magnetic field and gravity measurements. We'll never visit this region. No material we can engineer would survive the journey. Even the toughest spacecraft would be crushed long before reaching the metallic hydrogen ocean. So we study it indirectly, using mathematics and physics to model what we cannot see, building understanding from the shadows cast by what lies beneath. As you sink into sleep, sinking through layers of consciousness, imagine that descent through Jupiter, each layer stranger than the last, until you reach a place beyond all familiar experience. The winds on Jupiter are extreme. At the equator, jet streams flow eastward at speeds exceeding 400 miles per hour. That's faster than the strongest tornadoes on Earth, faster than any hurricane wind ever recorded. And these aren't brief gusts. They're sustained winds that flow continuously, year after year, century after century. Different latitudes have different wind speeds and directions. Near the equator, winds flow eastward, move toward higher latitudes, and you encounter westward flowing jets, then eastward again. The pattern alternates all the way to the poles, creating those distinctive bands we see in images. Each band is essentially a jet stream, a river of atmosphere flowing at hundreds of miles per hour. What drives these winds? Partly Jupiter's rapid rotation. The 10-hour day creates strong Coriolis forces that deflect moving air into east-west patterns. Partly the internal heat, which drives convection and creates pressure differences that air moves to equalize. And partly the lack of surface friction. On Earth, mountains and land masses slow winds, creating turbulence and breaking up large-scale patterns. Jupiter has no such obstacles. The wind can blow unimpeded, flowing in stable channels that persist for geological timescales. If you could somehow survive in Jupiter's atmosphere, floating in a balloon perhaps, at a level where pressure and temperature were survivable, you'd experience winds that would make Earth's most violent storms seem gentle. The air around you would be racing at hundreds of miles per hour, but you'd move with it, feeling relatively calm within your own wind band while watching adjacent bands flow in the opposite direction, creating shear zones of incredible turbulence where storms are born and die. Jupiter's atmosphere is always in motion, never still, never calm. It's a planet-sized engine converting heat into motion, thermal energy into kinetic energy, creating winds that dwarf anything terrestrial. As you lie still, breathing slowly, preparing for sleep, Jupiter's winds howl across thousands of miles, timeless and tireless, the breath of a giant that never stops. High in Jupiter's atmosphere, above the main cloud decks, there's a haze. It's subtle, often invisible light, but detectable in ultraviolet and infrared observations. This haze consists of tiny particles, complex organic molecules called hydrocarbons, made primarily of carbon and hydrogen atoms linked together in chains and rings. These molecules form through photochemistry. Methane gas, present in trace amounts throughout Jupiter's atmosphere, rises to high altitudes where it's exposed to ultraviolet light from the sun. UV photons have enough energy to break the chemical bonds holding methane molecules together, creating fragments, free radicals that are highly reactive. These fragments collide with other molecules and fragments, bonding together to form larger molecules. Ethane, acetylene, even more complex compounds like benzene or polycyclic aromatic hydrocarbons. These molecules eventually condense into tiny solid particles, creating a haze layer that gives Jupiter's upper atmosphere a slightly brownish or orange tint in some wavelengths. It's similar to smog on Earth, though created by natural processes rather than industrial pollution. The particles are small, perhaps a fraction of a micrometer across, but collectively they scatter and absorb light, affecting how we see the planet. This same chemistry happens on Saturn's moon Titan, where it creates an opaque orange haze so thick you can't see the surface through it. On Jupiter, the haze is much thinner, more translucent, but it's the same basic process. Sunlight plus simple molecules equals complex organic chemistry. The word organic doesn't necessarily mean biological. In chemistry, organic simply means carbon-based. These hydrocarbon hazes aren't alive, aren't products of life, but they are the kind of molecules that, under the right conditions, can serve as building blocks for more complex chemistry, potentially even prebiotic chemistry. Jupiter's atmosphere is an organic chemistry lab, constantly producing molecules that, on other worlds with different conditions, might participate in the chemistry of life. As you drift off, chemistry continues, molecules forming and breaking, the universe experimenting endlessly with combinations. Earth's seasons are dramatic because our planet is tilted 23.5 degrees relative to our orbital plane. This means that during summer, your hemisphere is tilted toward the sun, receiving more direct sunlight and experiencing longer days. During winter, it's tilted away, receiving less sunlight and enduring shorter days. Jupiter's axial tilt is only 3 degrees, barely tilted at all. This suggests Jupiter shouldn't have meaningful seasons, and yet observations show subtle seasonal changes. Why? The answer lies in Jupiter's elliptical orbit. While Earth's orbit is nearly circular, Jupiter's orbit has a slight eccentricity. At perihelion, the closest point to the Sun, Jupiter is about 460 million miles from the Sun. At aphelion, the farthest point, it's about 507 million miles away. This difference affects how much solar energy Jupiter receives. The seasonal changes are subtle. We're not talking about summer and winter in the human sense. No trees losing leaves, no ice ages and heat waves. But instruments can detect small variations in cloud altitude, storm activity, and atmospheric temperature that correlate with Jupiter's position in its orbit. These changes unfold slowly, since Jupiter takes nearly 12 Earth years to complete one orbit. A Jovian season lasts about 3 Earth years. There might also be internal seasonal cycles, variations in atmospheric circulation patterns that occur on different time scales. Jupiter's weather is complex enough that it likely has multiple overlapping cycles, some driven by orbital position, others by internal dynamics, creating a rich temporal structure that we're only beginning to map. The idea of seasons on Jupiter is strange. Seasons, to us, mean changing weather, shifting light, the cycle of growth and dormancy. On Jupiter, seasons are abstract, statistical variations in atmospheric parameters, detectable only through careful measurement. Yet they exist, proof that even worlds without obvious seasonal cues experience the rhythms of time, the subtle dance between planet and star that creates variation in the eternal return. Close your eyes and feel Earth's season around you, while Jupiter's longer, gentler seasons cycle in the darkness above. On Earth, the poles are dramatically colder than the equator. At the equator, you find rainforests and deserts, heat and humidity. At the poles, you find ice sheets and frozen tundra, temperatures that regularly drop far below zero. The temperature difference can be 50, 60, even 70 degrees Celsius between the warmest and coldest regions. Jupiter is different. Despite being so much larger, despite having such intense atmospheric dynamics, the temperature difference between equator and poles is only about 5 degrees Celsius. Measurements show the cloud tops are around 145 degrees Celsius, 230 Fahrenheit, at the equator, and perhaps 150 Celsius at the poles. A small difference, almost negligible. Why so uniform? The answer is Jupiter's internal heat. On Earth, the sun is our primary heat source. Solar heating is strongest at the equator, where sunlight hits most directly. Weakest at the poles, where sunlight arrives at a glancing angle. This creates the temperature gradient that drives our weather. But on Jupiter, internal heat is significant. Remember, the planet radiates more energy than it receives from the sun. This internal heat is distributed relatively evenly across all latitudes, warming the poles and preventing the steep temperature gradients we see on Earth. Additionally, Jupiter's rapid rotation and strong jet streams transport heat efficiently from equator to poles. The atmospheric circulation acts like a planetary heating system, redistributing warmth and preventing any region from becoming dramatically hotter or colder than the average. This uniformity means Jupiter's weather isn't driven primarily by equator to pole temperature differences the way Earth's is. Instead, it's driven by internal heat, rapid rotation, and the complex interactions between different wind belts. The result is a different kind of weather, one where latitude matters less than we'd expect, where the poles aren't dramatically different from the equator, at least in terms of temperature. As you warm yourself under blankets, achieving your own uniform temperature, Jupiter maintains its strange thermal equilibrium, nearly the same temperature from equator to pole. Water, H2O, the molecule of life on Earth, exists on Jupiter. This might seem surprising. Jupiter seems so alien, so unlike Earth, that we might not expect it to share such a familiar substance. But water is common in the universe. Hydrogen is the most abundant element. Oxygen is common too, and when you put them together in the right conditions, you get water. On Jupiter, water exists mostly as vapor and ice, not liquid. The temperatures and pressures where liquid water would be stable are buried deep in the atmosphere, far below the visible clouds. What we can detect from above are water-ice clouds, forming at altitudes where temperatures drop below freezing and pressure is low enough for clouds to condense. But here's the puzzle. We don't know how much water Jupiter has. Early measurements suggested less water than expected, leading to theories that Jupiter formed farther from the Sun than we thought, in a colder region where water ice was scarce. But more recent measurements from Juno show water abundances varying dramatically by location. Some regions have much more water than others. The deepest probe ever sent into Jupiter's atmosphere, the Galileo probe that descended in 1995, found surprisingly little water. But it may have entered through an unusually dry region, like a spacecraft landing in Earth's Sahara Desert and concluding our planet is dry. We need more measurements from different locations to understand Jupiter's true water content. Why does this matter? Water content tells us about Jupiter's formation, where it formed, what materials were available, whether it migrated inward from a more distant orbit. Water drives some of Jupiter's meteorology, creating clouds and precipitation deep in the atmosphere. And water is a key ingredient for life as we know it, making its presence or absence significant for understanding the potential habitability of Jupiter's moons. As you hydrate yourself before sleep, perhaps drinking water, Jupiter holds its own water, hidden deep, a familiar molecule in an alien world. How thick is Jupiter's atmosphere? The question seems simple but lacks a clear answer because there's no definite boundary where the atmosphere ends. If we define atmosphere as the gaseous envelope surrounding a planet, then Jupiter's atmosphere extends from the top of its clouds down to where? Where does gas become so compressed that it's more liquid than gas? That transition happens gradually, over hundreds or thousands of miles, without a sharp boundary. Some scientists define the atmosphere as the outermost 3,000 miles or so, the region where gas is still recognizably gas-like. Below that, the material becomes supercritical, a state where liquid and gas phases merge into something in between, a fluid that has properties of both. This supercritical region extends deeper still, perhaps another few thousand miles, before we reach the metallic hydrogen region. So the atmosphere might be 3,000 miles thick, or 6,000, or more, depending on how you define it. For comparison, Earth's atmosphere is considered to extend about 60 miles above the surface, though some traces of atmosphere reach hundreds of miles up. Jupiter's atmosphere is at least 50 times thicker than Earth's, possibly 100 times. A vast ocean of air that contains more mass than several Earth-sized planets combined. This thickness has consequences. Weather systems can be hundreds of miles tall. Convection currents can span vertical distances greater than Earth's diameter. Material can circulate between different pressure and temperature regimes, creating complex three-dimensional flows that we're only beginning to understand. Jupiter's weather isn't just a surface phenomenon. It's volumetric, occupying a three-dimensional space vast enough to swallow multiple Earths. As you breathe in sleep, your breath moving perhaps a foot from nose to lungs, Jupiter's atmosphere circulates across thousands of miles, from frozen cloud tops to hot supercritical depths. An endless cycle of rising and falling, a breath that began billions of years ago and will continue billions more. Earth has auroras, the northern and southern lights, shimmering curtains of green and red that dance across polar skies. When charged particles from the sun interact with our magnetic field and atmosphere, they're beautiful, ephemeral, appearing during strong solar activity and fading when the solar wind calms. Jupiter has auroras too, but they're different in almost every way. Jupiter's auroras are permanent. They never stop. While Earth's auroras require solar storms to trigger them, Jupiter's are constantly active, powered by the planet's own rotation and its interactions with its moons, particularly Io. As Jupiter's magnetic field sweeps past Io, it strips away particles from Io's volcanic eruptions, creating a plasma torus, a donut-shaped cloud of charged particles orbiting Jupiter. These particles spiral along magnetic field lines toward Jupiter's poles, slamming into the atmosphere and creating continuous auroras. The power output is staggering. Jupiter's auroras emit about 1,000 trillion watts of energy, more than the entire energy consumption of human civilization. They glow primarily in ultraviolet light, invisible to human eyes but brilliant in UV observations. If you could see ultraviolet, Jupiter's poles would shine like cosmic spotlights, beacons of energy that outshine almost anything else in the solar system except the sun. The auroras extend far above Jupiter's cloud tops, reaching altitudes of several hundred miles. The magnetic interactions are so complex that Jupiter's auroral emissions include not just UV light, but also radio waves. The same radio waves amateur astronomers detected in the 1950s, announcing Jupiter's presence across the electromagnetic spectrum. There's something humbling about this. A natural process occurring billions of miles away releases more energy than all of human industry, all of our power plants and engines and devices combined. Jupiter's auroras are a reminder of scale, of the vast energies at play in the cosmos, of how small our mightiest accomplishments remain compared to planetary processes. As you drift off, Jupiter's poles glow ceaselessly, light pouring into space, energy that no one witnesses, but that continues regardless. Beauty and power in the darkness. Magnetic fields are invisible, intangible things that we mostly notice through their effects. A compass needle turning toward north. Iron filings arranging themselves in elegant curves around a magnet. On Earth, our magnetic field is strong enough to deflect solar wind and create auroras, but it's relatively modest on the cosmic scale. Jupiter's magnetic field is a monster in comparison, about 20,000 times stronger at its source than Earth's field. This difference isn't just impressive numerically. It has profound consequences. Jupiter's magnetic field extends millions of miles into space, creating a magnetosphere, a bubble of magnetic influence that dwarfs anything in the solar system except the sun's own magnetic domain. If you could somehow see magnetic fields with your eyes, Jupiter would appear larger than the sun from Earth, a vast invisible structure filling the night sky. This powerful field is generated by that ocean of metallic hydrogen deep inside Jupiter, electrically conductive fluid spinning as the planet rotates. It's a planetary dynamo operating at a scale Earth can't match. Our metallic core is much smaller, our rotation only slightly slower, but the combination gives Earth a magnetic field that's protective but modest. Jupiter's field is overwhelming, dominating the space around it. The strength creates hazards. Charged particles trapped in Jupiter's magnetosphere are accelerated to nearly the speed of light, creating radiation belts far more intense than Earth's Van Allen belts. Spacecraft passing through this region must be specially hardened against radiation, and even so, they sustain damage. Several of Jupiter's moons orbit within this radiation zone, bombarded constantly by high-energy particles. Yet this field also protects Jupiter's moons in some ways, deflecting cosmic rays and solar wind that might otherwise strip away their atmospheres. It's a complex interaction. The magnetosphere is both weapon and shield, both hazard and haven. As you lie protected by Earth's modest magnetic field, invisible lines of force gently guiding away particles that would harm you, Jupiter's field roars, a titanic force shaping space for millions of miles, powerful beyond human scale. Let's contemplate size again, but this time not Jupiter itself, its magnetosphere. The magnetosphere is the region of space dominated by Jupiter's magnetic field, the volume within which Jupiter's magnetism is stronger than the Sun's magnetic influence. For Earth, this region extends perhaps 40,000 miles on the sunward side, where solar wind compresses it, and several times that distance on the night side, where it stretches into a long tail. Jupiter's magnetosphere is incomparably larger. On the sunward side, it extends roughly 2 million miles from the planet. On the night side, it stretches even farther, creating a magnetic tail that extends beyond Saturn's orbit when the planets are aligned. The tail is so long that when solar wind is calm, it might reach 400 million miles or more. If this magnetosphere were visible, if our eyes could see magnetic field lines, the way they see light, Jupiter would dominate the night sky. Even from Earth's distance, roughly 500 million miles away at closest approach, Jupiter's magnetosphere would appear about twice the angular size of the full moon. Imagine looking up and seeing not just a bright point of light, but a vast structure, a bubble larger than the moon, shimmering with trapped particles and flowing energy. The sky would tell a different story, one where Jupiter's presence was undeniable, overwhelming. Of course, we can't see magnetic fields with our eyes. The magnetosphere remains invisible, detectable only through instruments that measure magnetic field strength or observe the radio waves and particles interacting with it. But it's there, always, a structure larger than the sun, yet completely transparent to visible light. A realm of forces we understand mathematically, but can never directly experience. As you close your eyes, shutting out the visible world, imagine that invisible realm, magnetic fields curving and flowing, particles spiraling along field lines, energy transferring between solar wind and planetary magnetism, all of it happening silently, invisibly, in the space where we once thought nothing existed. The universe is full of things we cannot see, but that shape reality nonetheless. Earth's magnetic field is roughly aligned with its rotation axis. The magnetic North Pole is close to the geographic North Pole, which is why compasses work reasonably well for navigation. There's some offset, about 11 degrees, but it's modest. Jupiter's magnetic field is more complicated. The field is tilted about 10 degrees from Jupiter's rotation axis, similar to Earth, but it's also offset from the planet's center by about 10% of Jupiter's radius, roughly 4,300 miles. This offset creates asymmetry. One hemisphere experiences stronger magnetic fields than the other. The radiation belts are denser in some regions, sparser in others. As Jupiter rotates every 10 hours, the magnetosphere wobbles, pulsing and shifting as the offset field sweeps around. If you were a spacecraft orbiting Jupiter, the magnetic field strength you'd measure would vary dramatically depending on your position and the planet's rotation. Why is the field offset? It probably relates to the complex dynamics of the metallic hydrogen ocean deep inside. The dynamo that generates the field isn't centered perfectly, perhaps because convection currents are asymmetric, or because the core region has an irregular shape, or because there are multiple layers of circulation at different depths, creating interfering magnetic patterns. We don't fully understand the details, but the offset tells us that Jupiter's interior is more complex than a simple uniform sphere of conducting fluid. This complexity means Jupiter's magnetosphere is dynamic, constantly changing as the planet rotates. Particles trapped in the radiation belts experience varying conditions, sometimes compressed, sometimes relaxed. The auroras pulse and shift with the 10-hour rotation period. Even Jupiter's radio emissions, those crackling bursts that radio telescopes detect, are modulated by the rotation, creating a lighthouse effect as the offset field sweeps around. Jupiter's magnetism isn't static. It breathes and pulses with the planet's spin, a living thing in some metaphorical sense, animated by rotation and internal circulation, never still, never truly at rest. How do planets generate magnetic fields? The answer is the dynamo effect, a process where moving electrically conductive fluid creates electric currents, and those currents create magnetism. On Earth, the dynamo operates in our liquid iron outer core. Iron conducts electricity well, and the core's convection, driven by heat escaping from the even deeper solid inner core, creates circulating currents that generate Earth's magnetic field. Jupiter's dynamo operates on a grander scale. Instead of a relatively small core of liquid iron, Jupiter has an entire ocean of metallic hydrogen, a layer thousands of miles thick containing more mass than many planets. This metallic hydrogen conducts electricity, and as Jupiter rotates rapidly, the fluid is set into complex motion. Convection driven by internal heat creates vertical flows. The Coriolis effect from rotation deflects these flows into spiraling patterns. The combination of rotation and convection creates organized currents that flow through the conducting fluid. These currents, like any current flowing through a conductor, create magnetic fields. The fields reinforce each other, amplifying through positive feedback until they reach equilibrium. Strong enough to affect the fluid's motion, but constrained by the energy available from the planet's rotation and internal heat. The result is Jupiter's enormous magnetic field, sustained continuously by the dynamo as long as the metallic hydrogen keeps moving. This is one of those processes that's easy to describe in principle, but fiendishly difficult to model in detail. The equations governing magnetohydrodynamics, the interaction of magnetic fields and conducting fluids, are nonlinear and complex. Simulating a planetary dynamo requires supercomputers running for weeks, and even then we can only approximate what's happening. Jupiter's dynamo has been operating for billions of years, a natural computer solving these equations in real time, generating a field whose details we're still working to understand. As you drift off, Jupiter's metallic ocean continues its ancient circulation, currents flowing, magnetism emerging, a process older than multicellular life on Earth, timeless and patient. Magnetic fields can trap charged particles, electrons, protons, ions, forcing them to spiral along field lines. Earth's Van Allen radiation belts work this way. Particles from the solar wind get caught in Earth's magnetosphere, spiraling back and forth between the poles, creating zones of increased radiation that satellites must navigate carefully. Jupiter has similar radiation belts, but they're vastly more intense. particles in Jupiter's magnetosphere can be accelerated to nearly the speed of light, not quite reaching that ultimate cosmic speed limit, but close enough that relativistic effects become important. These particles carry enormous energy. When they strike matter, a spacecraft's electronics, for instance, they cause damage. Ionizing radiation disrupts computer chips, degrades solar panels, can even trigger false commands or memory errors in spacecraft computers. NASA's Juno spacecraft, designed to study Jupiter from close orbit, had to be specially built to withstand this radiation. Its electronics are housed in a titanium vault, a protective box designed to shield sensitive instruments from the particle bombardment. Even so, Juno's mission is limited partly by radiation damage. Eventually, enough cumulative exposure will degrade its systems beyond repair. The radiation is particularly intense near Io's orbit. Io, constantly spewing volcanic material into space, provides a steady supply of particles, sulfur and oxygen ions stripped from Io's atmosphere and trapped by Jupiter's magnetic field. These particles accumulate in a structure called the Io plasma torus, a donut-shaped cloud of charged material orbiting Jupiter. From there, they're accelerated by electromagnetic interactions, gaining energy until they become dangerous, high-speed projectiles. For any future missions to Jupiter's moons, especially Europa with its potentially habitable ocean, this radiation is a major challenge. Spacecraft will need heavy shielding. Landing missions may need to be brief. Even robotic explorers will have limited lifetimes in this environment. Jupiter's magnetosphere, for all its scientific interest, is hostile to visitors, a realm of energies that would quickly destroy unprotected technology or biology. As you rest safely, shielded by Earth's atmosphere and distance from cosmic hazards, Jupiter's radiation belts rage, timeless and lethal. In 1955, astronomers Bernard Burke and Kenneth Franklin were studying cosmic radio sources using a large radio antenna when they noticed something unexpected. Periodic bursts of radio emission that seemed to come from the direction of Jupiter. At first, they doubted their instruments. Planets weren't supposed to emit strong radio waves, but the signals persisted, repeating with a roughly 10-hour period, Jupiter's rotation period. The conclusion was inescapable. Jupiter was broadcasting. This was revolutionary. Before then, astronomers studied planets primarily through visible light, what we could see with telescopes. Suddenly, Jupiter announced itself in a completely different part of the electromagnetic spectrum. The radio emissions we now know are generated by electrons spiraling along Jupiter's magnetic field lines at near light speed. As they spiral, they emit synchrotron radiation, a type of electromagnetic radiation that includes radio waves. The emissions aren't constant. They come in bursts, sometimes lasting minutes, sometimes hours. The intensity varies with Jupiter's rotation and with Io's position. When Io's at certain locations in its orbit, the radio emissions intensify, another clue that Io's volcanic activity and the resulting plasma torus are involved in the process. Amateur radio astronomers with relatively simple equipment can still detect Jupiter's radio emissions today. You don't need a professional observatory or expensive instruments. A basic radio telescope tuned to frequencies around 20 megahertz can pick up Jupiter's voice, crackling, hissing bursts of noise that sweep across the sky as the planet rotates. It's a reminder that the universe communicates in many wavelengths, not just the visible light our eyes perceive. Listening to Jupiter's radio emissions is an almost meditative experience. The sounds, converted from radio waves into audio frequencies humans can hear, are alien, mechanical, yet somehow organic. Whistles and pops, hisses and roars, the electromagnetic song of a planet's magnetosphere interacting with its moons and the solar wind. As you drift towards sleep, Jupiter continues broadcasting, its radio voice crossing the solar system. A message with no intended recipient, just the natural consequence of magnetic fields and high-energy particles, physics made audible. Jupiter's magnetosphere isn't static. It changes size and shape depending on conditions in the solar wind, the stream of charged particles flowing outward from the sun. When the solar wind is strong, when a solar storm sends a burst of particles and magnetic field toward Jupiter, the pressure compresses Jupiter's magnetosphere, pushing it inward. The sunward side might shrink from 2 million miles to 1.5 million miles, squeezing like a balloon being compressed. When solar wind is calm, the magnetosphere expands, stretching outward as Jupiter's magnetic pressure overcomes the external pressure from the solar wind. The magnetosphere breathes, expanding and contracting with the rhythms of solar activity, responding to gusts and lulls in the solar wind like a sail responding to changes in the breeze. This breathing has consequences. When the magnetosphere is compressed, the trapped particles are squeezed closer together, increasing the radiation belt intensity. The auroras brighten. Radio emissions intensify. It's as if Jupiter becomes temporarily more agitated, its magnetosphere responding to the provocation of solar activity. Conversely, during calm periods, the magnetosphere relaxes, becoming more diffuse. The radiation belts spread out. The system settles into a quieter state, though quiet is relative. Even at its calmest, Jupiter's magnetosphere is far more active and intense than Earth's. This dynamic behavior makes Jupiter's magnetosphere a living laboratory for studying space plasma physics. The same processes that occur at Jupiter, magnetic reconnection, particle acceleration, shockwave formation, also occur at Earth, around other planets, and in astrophysical contexts like accretion disks around black holes or stellar coronas. Jupiter is accessible enough to study in detail, dynamic enough to display a wide range of phenomena, and extreme enough that effects visible only weakly at Earth become dominant there. As you breathe in sleep, slow and regular, Jupiter's magnetosphere breathes too, faster and more erratically, pulsing with the 10-hour rotation and the variable pressure of the solar wind. Earth's magnetic field has reversed many times throughout geological history. North becomes south, south becomes north. These reversals are recorded in rocks. Iron minerals align with the magnetic field as rocks form, preserving a snapshot of the field's direction. By studying these magnetic records, geologists have determined that Earth's field reverses every few 100,000 years on average. Though the timing is irregular, Jupiter's field also reverses, though we can't directly observe these reversals happening. They occur on timescales too long for human observation. Instead, we infer them from theoretical models of how dynamos behave, and from observations of Jupiter's moons. Some of Jupiter's moons, particularly Ganymede, have magnetized rocks on their surfaces. These rocks formed billions of years ago and preserved the direction of Jupiter's magnetic field at that time. By studying these ancient magnetic signatures, scientists can piece together a history of Jupiter's field behavior. The reversals aren't periodic. They don't happen on a regular schedule. Instead, they emerge from the chaotic dynamics of the dynamo, moments when the circulation patterns in the metallic hydrogen ocean reorganize themselves, flipping the field's polarity. Between reversals, the field might remain stable for millions or tens of millions of years. Then, relatively suddenly, though suddenly might mean thousands of years, the field weakens, becomes disorganized, and reestablishes itself with opposite polarity. During a reversal, the field strength drops significantly. The magnetosphere would shrink. Radiation belt particles might escape. The moons would be more exposed to cosmic rays and solar wind. Then the field rebuilds, growing stronger with its new orientation, until eventually, perhaps millions of years later, it reverses again. These reversals are reminders that even seemingly permanent features of planets are temporary on geological timescales. Jupiter's field, so dominant and powerful now, has been oriented differently in the past and will be again in the future. Nothing is truly eternal. Everything cycles, shifts, transforms. As you drift through your own cycles, waking and sleeping day after day, Jupiter cycles too, on time frames that dwarf human existence. Jupiter doesn't travel through space alone. It's accompanied by a retinue of at least 95 moons, small worlds, captured asteroids, chunks of rock and ice orbiting the giant planet. That number, 95, isn't final. New tiny moons are discovered regularly as telescope technology improves and survey programs detect ever fainter objects. By the time you hear this, the count might be higher. Most of these moons are small, irregular chunks of rock, probably asteroids that wandered too close to Jupiter and were captured by its gravity. Some are barely a mile across, tumbling fragments orbiting in distant, elongated paths. These outer moons take years to complete a single orbit, and many travel retrograde, backward, opposite to Jupiter's rotation. This retrograde motion confirms they weren't formed with Jupiter, but captured later, their orbits shaped by the chaotic gravitational interactions of the early solar system. But Jupiter's four largest moons, the Galilean moons, Io, Europa, Ganymede, and Callisto, are worlds in their own right. Each is large enough that if it orbited the Sun directly, it would be classified as a planet. Ganymede is bigger than Mercury. Europa, though smaller, has more water than Earth. These aren't just moons. They're planetary bodies, complex and geologically active, each with its own story. The total mass of all Jupiter's moons is tiny compared to Jupiter itself, less than 1/10,000th of the planet's mass. Jupiter is so dominant that its moons are barely more than cosmic dust by comparison. And yet, these moons are what make Jupiter truly fascinating for astrobiology and planetary science. The planet itself is unlikely to harbor life. Too hot, too turbulent, no stable environment. But the moons, particularly Europa with its subsurface ocean, might be habitable. Jupiter's system is like a miniature solar system, with the planet playing the role of the Sun and the moons as orbiting worlds. As you close your eyes, 95 moons circle Jupiter. Some close enough to complete orbits in hours, others so distant they take years. A complex gravitational dance that's been ongoing for billions of years. On January 7, 1610, Galileo Galilei pointed his improved telescope at Jupiter and saw something that would change astronomy forever. 3 small stars arranged in a line near the planet. He sketched what he saw. The next night, they'd moved. More observations over subsequent nights revealed 4 objects orbiting Jupiter. Not stars at all, but moons. Galileo named them the Medicean stars after his patrons, but history has given them different names. Io, Europa, Ganymede, and Callisto, figures from Greek mythology associated with Zeus, Jupiter's Greek equivalent. Collectively, we call them the Galilean moons, honoring the man who first recognized them as satellites of another planet. These 4 moons are extraordinary. Io is the most volcanically active body in the solar system, its surface constantly renewed by eruptions. Europa hides a global ocean beneath its icy shell, making it one of the most promising places to search for extraterrestrial life. Ganymede is the largest moon in the solar system, with its own magnetic field. Callisto is ancient and cratered, preserving a 4 billion year record of impacts. Each moon has a distinct personality, a unique character shaped by its distance from Jupiter and its interactions with the other moons. They're locked in orbital resonance. Io orbits 4 times for every 2 orbits of Europa and every 1 orbit of Ganymede. This mathematical relationship isn't coincidental. It's stable, maintained by gravitational interactions that have lasted billions of years. The Galilean moons aren't just interesting in themselves. They're laboratories for studying tidal forces, orbital dynamics, planetary formation, and the potential for life beyond Earth. They're accessible, close enough that we've sent multiple spacecraft to study them, far enough that they remain mysterious and incompletely explored. As you drift off, these 4 worlds circle Jupiter, Io erupting, Europa's ice fractured above a hidden sea, Ganymede serene with its magnetic cocoon, Callisto ancient and patient, all of them spinning in gravitational harmony, a system within a system, moons around a giant around a star. Ganymede holds multiple records. It's the largest moon in the solar system, bigger than our own moon, bigger than Pluto, even bigger than the planet Mercury. With a diameter of 3,270 miles, Ganymede is substantial enough that if it orbited the Sun instead of Jupiter, we'd classify it as a planet without hesitation. But it's Jupiter's moon, forever relegated to satellite status, despite its planetary size. What makes Ganymede truly unique among moons is its magnetic field. It's the only moon known to have its own magnetosphere, a miniature version of what planets like Earth and Jupiter possess. This tells us something important about Ganymede's interior. It must have a liquid, electrically conductive layer, probably a subsurface ocean of salty water, deep beneath the ice, and a partially molten metallic core. The combination creates a dynamo, generating magnetism. Ganymede's magnetosphere exists within Jupiter's much larger magnetosphere, creating a nested structure, a magnetic bubble within a bubble. The 2 fields interact in complex ways. Sometimes they reinforce each other, sometimes they compete. Ganymede's field provides some protection from Jupiter's intense radiation, creating a slightly less hostile environment on parts of the moon's surface. Though less hostile is relative, it's still bombarded by high-energy particles. The surface is a patchwork of dark, ancient terrain, heavily cratered from billions of years of impacts, and lighter, younger terrain with grooves and ridges suggesting geological activity in Ganymede's past. Perhaps the moon experienced a period of tectonic activity, the icy crust fracturing and shifting, or perhaps impacts from comets or asteroids melted parts of the surface, allowing fresh ice to resurface. Beneath that surface, Ganymede might have an ocean, containing more water than all of Earth's oceans combined. The ocean would be sandwiched between layers of ice, normal ice above, high-pressure ice below, kept liquid by tidal heating from Jupiter and the warmth of Ganymede's core. A hidden sea, dark and cold, existing in complete isolation from the universe above. As you rest, Ganymede orbits silently, the largest moon, alone possessing magnetism, holding secrets beneath its ancient scarred face. Europa appears in images as a smooth, white marble, its surface crisscrossed with reddish-brown lines, like veins or cracks. It's one of the smoothest objects in the solar system, with very few impact craters. This tells us immediately that the surface is young, geologically speaking. Something is refreshing Europa's face, erasing craters, renewing the ice. That something is the ocean beneath. Europa has a global ocean of liquid water, tens of miles deep, lying beneath an ice shell perhaps 10 to 15 miles thick. The ice is water ice, not exotic high-pressure ice, but ordinary frozen water, the same stuff that forms in your freezer. Beneath that ice, liquid water exists at near freezing temperatures, but prevented from freezing by the slight warmth from Europa's interior, and perhaps dissolved salts that lower the freezing point. How do we know the ocean exists if we can't see it? Multiple lines of evidence converge. Europa's magnetic signature, consistent with the conducting layer. Salty water conducts electricity. The way Europa deforms slightly as Jupiter's gravity flexes it, suggesting a liquid layer decoupled from the solid core. The ice's structure and the pattern of cracks, indicating the shell floats on something fluid, and plumes of water vapor observed erupting from the surface, possibly geysers from the ocean below breaking through thin spots in the ice. This ocean might contain twice as much water as all of Earth's oceans combined. Imagine that, a moon smaller than our own, with more water than our entire planet. The ocean is global, covering Europa entirely, unlike Earth where oceans occupy 70% of the surface. If you could melt Europa's ice shell, you'd have a water world, an ocean perhaps 40 to 100 miles deep, covering the entire moon. The ocean is dark. No sunlight penetrates the ice. If life exists there, it would be blind or adapted to other senses: chemical, thermal, tactile. The ocean floor might have hydrothermal vents like Earth's, places where water seeps down, gets heated by the rocky mantle, and returns enriched with minerals and chemicals. On Earth, such vents support entire ecosystems independent of sunlight. Could the same be true on Europa? As you drift into sleep's darkness, Europa's ocean remains dark too, a hidden sea that may teem with life or remain sterile. We don't yet know. If Europa is the water world, Io is the fire world. It's the most volcanically active object we've ever discovered, with hundreds of active volcanoes erupting at any given time. Some eruptions are small, gentle effusions of lava. Others are explosive, hurling sulfur and sulfur dioxide hundreds of miles above the surface into space. Plumes from the most powerful eruptions can be seen from Earth-orbiting telescopes, frozen fountains of material caught in the act of escaping Io's weak gravity. Io's surface is constantly renewed. Impact craters, which scar nearly every other solid body in the solar system, are almost completely absent on Io. They don't have time to accumulate before volcanic activity buries them under fresh lava. The surface is young, perhaps only 1 million years old on average, meaning that the Io we see today looks nothing like the Io of 1 million years ago, and will look different again 1 million years hence. Why is Io so active? Tidal heating. Io orbits close to Jupiter, and the gravitational pull is immense. But Io's orbit isn't perfectly circular. It's slightly elliptical, forced into that shape by gravitational interactions with Europa and Ganymede. As Io moves closer to and farther from Jupiter during each orbit, the tidal forces vary, flexing the moon like you might squeeze a stress ball. This constant flexing generates heat through friction, melting Io's interior and driving the volcanic activity. The result is a moon that glows. Io's volcanoes are so hot that they emit significant infrared radiation, enough that sensitive infrared telescopes can detect Io's heat from Earth. The moon is literally glowing with internal fire, a cosmic forge constantly erupting, reshaping, renewing itself. The landscape is alien: yellows, oranges, reds, whites, colors created by sulfur compounds deposited by volcanic eruptions. Black lava flows contrast with bright sulfur dioxide frost. It's a world painted by volcanism, a world that never rests. As you lie still, preparing for sleep, Io erupts. Lava flows across its surface. Plumes spray into space. The moon continues its restless existence, never calm, never quiet, forever churning with the energy of tidal forces that won't cease for billions of years. Fire incarnate, orbiting ice and water all around the giant. Europa's ocean might not be completely sealed. In 2013, astronomers using the Hubble Space Telescope detected something unexpected: plumes of water vapor erupting from Europa's southern hemisphere, reaching altitudes of perhaps 100 miles above the surface before falling back down. The discovery was tentative at first. The plumes are intermittent, not always present. But subsequent observations have confirmed them, and NASA's Juno spacecraft has detected fresh evidence of ongoing plume activity. These plumes are significant for multiple reasons. First, they confirm that Europa's ice shell has cracks or weak points where subsurface water can reach the surface. Second, they provide a potential way to sample Europa's ocean without having to drill through miles of ice. A spacecraft could fly through the plumes, collecting particles, and analyze them to determine the ocean's composition, its salinity, its chemistry, whether organic molecules are present. The plumes might be geysers, similar to the geysers in Yellowstone or Iceland, where water heated by geological activity forces its way to the surface. Or they might be cryovolcanism, ice volcanoes where liquid water or slushy ice erupts through cracks. On Earth, geysers are relatively gentle, liquid water boiling and spraying upward. On Europa, the near vacuum at the surface means water immediately vaporizes, expanding rapidly and propelling material much higher than terrestrial geysers could. The plume's existence hints at dynamic activity. Europa isn't a dead, frozen world. It's active, with material circulating between the ocean and the surface. This circulation might bring nutrients from the rocky ocean floor up toward the ice, or carry oxidants from the surface down to the ocean, potentially creating chemical gradients that could support life. Future missions are planned to fly through these plumes. NASA's Europa Clipper, launching in the 2020s, will carry instruments designed to analyze plume material. We might get our first taste of Europa's ocean without ever landing, sampling water that was days or hours earlier, part of that hidden sea. As you breathe in sleep, Europa exhales, plumes jetting into space, water from a hidden ocean briefly touching vacuum before falling back like snow, settling onto ice that hides the sea below. If Io is the youngest surface and Europa is being constantly refreshed, Callisto is the ancient one, the keeper of history. Callisto's surface is saturated with impact craters, marked by billions of years of collisions with asteroids and comets. Every square mile has been struck multiple times. New impacts obliterate old craters, which themselves obliterated even older craters, creating a palimpsest of overlapping scars. This heavily cratered appearance tells us that Callisto's surface is old, perhaps 4 billion years old, nearly as old as the solar system itself. Unlike Io, which is constantly resurfaced by volcanism, or Europa, which seems to renew its ice shell every few tens of millions of years, Callisto has remained geologically dead, or nearly so for most of its existence. The surface we see today looks much as it did billions of years ago, during the late heavy bombardment, when the inner solar system was still being cleared of debris left over from planet formation. Callisto orbits farther from Jupiter than the other Galilean moons, beyond the strong tidal forces that heat Io and Europa. It experiences less gravitational flexing, less internal heating. Its interior likely differentiated, partially, heavier materials sinking toward the center, but perhaps not completely. It may have a mixture of rock and ice throughout, never fully melting and separating like Earth's core and mantle did. And yet, even Callisto might have an ocean. Magnetic measurements suggest a conducting layer beneath the surface, possibly a salty subsurface ocean, similar to Europa's, but deeper and more isolated. If so, it would be one of the most isolated environments imaginable, buried beneath tens of miles of ice and rock, completely cut off from the surface for billions of years, existing in utter darkness and stillness. Callisto is the quiet one, the patient one. While Io erupts and Europa cracks, Callisto simply exists, bearing its scars, preserving a record of the solar system's violent youth. As you rest, Callisto orbits steadily, ancient and scarred, holding memories of impacts from when Earth was young, when life was just beginning, when the solar system was still finding its current configuration. Some things endure, some surfaces remember. The Galilean moons don't orbit randomly. They're locked in a precise mathematical relationship called orbital resonance. For every orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. The ratio is 4.2.1, a perfect harmony maintained for billions of years. This resonance isn't coincidental. It evolved through gravitational interactions over time. When moons orbit a planet, they exert tiny gravitational tugs on each other. Usually these tugs average out, having no long-term effect. But if the orbital periods are close to a simple ratio, 2:1, 3:2, 4:2:1, the tugs reinforce each other at regular intervals, creating a feedback loop. Small perturbations push the moons toward exactly matching the resonant ratio, and once locked in, the configuration becomes stable. This resonance has consequences. It forces Io's orbit to remain slightly elliptical, preventing tidal forces from circularizing it completely. The elliptical orbit means Io experiences varying tidal stress as it moves closer to and farther from Jupiter each orbit, generating the heat that drives its volcanism. Without the resonance, Io might have circularized its orbit over time, reducing tidal heating and becoming geologically dead. The resonance keeps Io active. Similarly, Europa's orbit is kept slightly elliptical, generating enough tidal heating to maintain its subsurface ocean. Ganymede, being farther out, experiences less tidal heating, but still enough to possibly maintain a deep ocean. The resonance is stable on billion-year timescales. It survived the late heavy bombardment, survived whatever catastrophes befell the solar system during its formation. The moons will maintain this relationship until something dramatic disrupts it. Perhaps in several billion years, when Jupiter's evolving interactions with the other giant planets might destabilize the system, or when the Sun becomes a red giant and alters the dynamics of the entire solar system. For now, the Galilean moons dance their mathematical dance, 4 orbits of Io for every 2 of Europa for every 1 of Ganymede, a cosmic waltz playing out in the silence of space, precision emerging from chaos, order maintained by gravity's invisible hand. As you drift off, they continue orbiting in perfect synchrony, a clockwork carved from worlds. Look closely at images of Europa, and you'll see its most distinctive feature: reddish-brown lines crisscrossing the white ice, some straight, some curved, some branching like veins or cracks in old porcelain. These are fractures, places where Europa's ice shell has split apart. Some cracks are narrow, just dark lines. Others are wide bands, sometimes with parallel ridges running alongside them. How do these cracks form? Tidal forces are the primary culprit. As Europa orbits Jupiter, the tidal stress varies, flexing the ice shell. Ice is brittle when cold, and Europa's surface is extremely cold, around 260 degrees Fahrenheit. Under stress, the ice fractures. Once a crack opens, warmer material from below, perhaps liquid water, perhaps slushy ice, can well up into the crack. When exposed to the surface cold and vacuum, it quickly freezes, creating ridges along the crack's edges. Some of Europa's features suggest the ice shell is moving, floating on the ocean like ice floes on an Arctic sea. Blocks of ice seem to have separated, rotated, and refrozen in new positions, a process called chaos terrain. This implies the ice shell is relatively thin in places, perhaps only a few miles thick, floating freely on the liquid ocean rather than being frozen solid all the way down to the rocky core. The reddish-brown color of the cracks is intriguing. It might be sulfur or sulfur compounds deposited by radiation processing, charged particles from Jupiter's magnetosphere striking the ice and chemically altering it. Or it might be salts, magnesium sulfate or sodium chloride, brought up from the ocean and deposited on the surface where they're irradiated and turn reddish. If the latter, these cracks represent samples of the ocean, frozen in place, accessible to study from orbit or eventually from landers. Europa's face is a map of stress and renewal, a record of the ice shell responding to Jupiter's gravity and the hidden ocean's movements. Each crack tells a story of fracture and healing, breaking and refreezing. As you drift towards sleep, your mind fractured by the day's stresses, Europa's ice cracks and heals, an endless cycle of breaking and mending. Io doesn't look like any other world. While most moons are gray or tan, rock and ice, Io is a riot of color. Yellows, oranges, reds, with patches of white and black. It looks more like a pizza or a diseased eyeball than a moon, a description first used by Voyager scientists when they saw the first close-up images in 1979, and remains apt today. The colors come from sulfur and sulfur dioxide. Io's volcanoes erupt both silicate lava, like Earth's volcanoes, and sulfur-rich materials. Elemental sulfur can appear in various colors, depending on temperature and allotropic form: yellow, orange, red, even green. Sulfur dioxide frost is white. When erupted onto Io's cold surface, these materials freeze and accumulate, painting the landscape. The volcanic plumes themselves can be seen in images, frozen in time by spacecraft cameras. Some plumes are symmetric umbrellas of material arcing up and falling back down. Others are more chaotic, jets of material shooting sideways or upward at various angles. The largest plumes reach hundreds of miles high before material falls back to the surface, slowly, in Io's low gravity. This constant deposition of volcanic material means Io's surface is always changing. Features visible in images from one spacecraft flyby may be altered or buried by the time the next spacecraft passes. Lava flows hundreds of miles long spread across the surface. Volcanic calderas, collapsed pits where magma has drained away, dot the landscape, and the colors shift as new material is deposited over old. Io also has mountains, surprisingly. Not volcanic mountains, but tectonic ones, formed by compression and uplift as the constant volcanic activity stresses the crust. Some of Io's mountains are taller than Mount Everest, jagged peaks rising above the volcanic plains, remnants of older crust that haven't yet been buried. It's a violent, dynamic world, constantly renewing itself, constantly erupting. If you could stand on Io, impossible due to radiation and the vacuum, you'd see an alien landscape of color and motion, geysers erupting silently in the airless environment, lava glowing red against the yellow sulfur plains, Jupiter dominating the sky above. As you close your eyes, Io never does. Its volcanoes burning ceaselessly, painting the moon in colors Earth rarely sees. Calling it an atmosphere is generous. Ganymede's atmosphere is so thin that it's barely more than a trace of gas, millions of times less dense than Earth's atmosphere. You couldn't breathe it. There's not enough to fill your lungs, and the pressure is so low that, exposed to it, your blood would boil. But it exists, and remarkably, it's oxygen. How does a moon get an oxygen atmosphere? Not through biology. There's no photosynthesis happening on Ganymede's frozen surface. Instead, the oxygen is created by radiolysis, a process where high-energy particles from Jupiter's magnetosphere strike water ice molecules on Ganymede's surface, breaking them apart. Water, H2O, splits into hydrogen and oxygen. The hydrogen, being lighter, escapes into space relatively quickly. The oxygen, being heavier, lingers longer, creating a very thin atmosphere. This oxygen atmosphere isn't uniform. It's probably denser near the poles, where Jupiter's magnetic field channels more charged particles, increasing the rate of radiolysis. And it's variable, waxing and waning as Ganymede orbits through different regions of Jupiter's magnetosphere. Ganymede isn't the only moon with an oxygen atmosphere created this way. Europa also has traces of oxygen from the same process. These oxygen atmospheres are products of ice and radiation, water being slowly destroyed and its components separated. Over billions of years, this process has stripped away some of the surface ice, gradually eroding Ganymede's outer layers. In a sense, Ganymede is surrounded by the ghosts of water molecules, broken apart by radiation and lingering briefly before escaping to space or freezing back onto the surface. It's an atmosphere of destruction, created by violence at the molecular level, sustained only by the continuous bombardment of high-energy particles. As you breathe deeply in sleep, pulling oxygen into your lungs, oxygen created by photosynthesis billions of years ago, Ganymede's oxygen drifts in near vacuum, a byproduct of radiation, thin and ephemeral, present but barely so. Beyond the Galilean moons, Jupiter's satellite system becomes more chaotic. There are dozens of smaller moons, most just a few miles across, orbiting at various distances and inclinations. These moons fall into groups, families based on orbital characteristics that suggest common origins. The inner moons, Métis, Adrastea, Amalthea, Thebe, orbit close to Jupiter, within its ring system, all traveling in the same direction as Jupiter's rotation, prograde. These are probably captured asteroids or fragments from larger bodies that broke apart, perhaps due to impacts or tidal stress. Then there are the irregular outer moons, orbiting far from Jupiter in elongated, inclined orbits. Some of these are prograde, traveling in the same direction as Jupiter's rotation, but many are retrograde. They orbit backward, opposite to Jupiter's spin. Retrograde orbits are dynamically unusual and suggest these moons weren't formed alongside Jupiter. Instead, they were captured, asteroids that wandered too close and were trapped by Jupiter's gravity. The retrograde moons cluster into families with similar orbital characteristics, suggesting they might be fragments of larger bodies that broke apart after capture. Perhaps a single large asteroid was captured by Jupiter, then later shattered by an impact or tidal stress, creating a family of smaller moons that still share similar orbits. These outer moons take years to complete a single orbit. Some have orbital periods of 700 days or more, nearly 2 Earth years just to go around Jupiter once. Their orbits are so elongated that they spend most of their time far from Jupiter, only occasionally swooping relatively close before retreating again. Jupiter's moon system is a gravitational archive, a collection of captured objects representing the asteroid population from different eras of solar system history. Some moons might be pristine samples from the outer asteroid belt. Others might be fragments of larger bodies that no longer exist. As you drift off, these distant moons continue their slow, elongated orbits, some traveling forward, some backward, all held by Jupiter's gravity, cosmic captives orbiting a giant forever. Not all moons are worlds. Some are barely more than boulders, irregular chunks of rock a mile or two across, tumbling end over end as they orbit Jupiter. These tiny moons lack the mass to pull themselves into spherical shapes. Gravity isn't strong enough to overcome the structural strength of rock at this scale, so they remain jagged, irregular, potato-shaped objects, fragments that might once have been part of larger bodies. These small moons are difficult to observe. They're dark, reflecting only a small percentage of the sunlight that hits them, and they're far from Jupiter, often hundreds of thousands or millions of miles away. Discovering them requires powerful telescopes and patient observation, watching for faint points of light that move against the background stars in ways consistent with orbiting Jupiter. Some were discovered only recently. As telescope technology improves, as survey programs systematically scan the space around Jupiter, new moons continue to be found. Each discovery adds to Jupiter's count, pushing the total higher. There might be dozens more still undiscovered, too small or too distant for current telescopes to detect. What are these tiny moons made of? Probably rock and metal, similar to asteroids. They're likely captured objects, asteroids that approached Jupiter at just the right angle and speed to be gravitationally snared rather than flung away or pulled into a collision course. The capture process is delicate. Most asteroids that approach Jupiter either pass by or crash into the planet or one of its larger moons. Only a small fraction end up in stable orbits. These moons are time capsules, in a sense, preserving material from the early solar system, unlike the Galilean moons, which have been heated and geologically processed. These tiny captured asteroids remain largely unchanged since their formation. They're samples of the ancient asteroid belt, brought close enough to study without needing to travel all the way to the belt itself. As you drift toward sleep, these cosmic pebbles tumble through darkness, small enough to fit inside a city, yet each a world unto itself, each with its own slow orbit around the giant. Amalthea is one of Jupiter's inner moons, orbiting between Io and Europa, though much closer to Jupiter than either. It's irregularly shaped, about 155 miles long, and has a distinct reddish color. For a long time, scientists wondered why. Most asteroids and small moons are gray or brownish, the natural color of rock and carbonaceous material. What makes Amalthea red? The answer is Io. Io's constant volcanic eruptions don't just reshape Io itself, they affect the entire inner Jupiter system. Sulfur and sulfur dioxide particles escape from Io's weak gravity, particularly from the most powerful volcanic plumes. Once in space, these particles become ionized by Jupiter's radiation environment and get swept up by the planet's magnetic field. They form a torus, a donut-shaped cloud, of material orbiting Jupiter at roughly Io's distance. Some of this material spirals inward or outward due to electromagnetic interactions, eventually raining down on other moons. Amalthea, orbiting within this zone of Io-derived material, gets coated with sulfur compounds over time. Millions of years of accumulation have painted Amalthea red, a second-hand coloring derived from its volcanic neighbor. This process affects other inner moons too. Thebe, another small moon orbiting near Amalthea, also shows reddish coloration. It's a reminder that moons in a system don't exist in isolation. They interact, exchange material, influence each other's environments. Io's volcanism shapes not just Io, but the space around Jupiter, the magnetosphere's composition, and the surfaces of neighboring moons. Amalthea is being painted in slow motion, one sulfur atom at a time, its surface gradually reddening as millennia pass. It's a cosmic artwork, created not by intention, but by the simple physics of particles and orbits, volcanic eruptions, and magnetic fields. The universe creates beauty incidentally, as a byproduct of processes that have no aesthetic goal, yet produce results we find striking. As you rest, Amalthea continues absorbing Io's cast-off material, gradually deepening its red hue, a process that will continue as long as Io erupts and Jupiter's magnetosphere spins. Here's a humbling statistic. If you added up all 95 of Jupiter's moons, the massive Galilean satellites, the inner moons, all the captured asteroids, their combined mass would still be less than 1/10,000th of Jupiter's mass. Even Ganymede, the largest moon, contributes only a tiny fraction. Jupiter is so overwhelmingly dominant that its entire retinue of satellites barely registers against its bulk. To put this in perspective, Earth's moon is about 1/81st of Earth's mass, a much more significant fraction. Our moon actually has enough gravitational influence to create substantial tides in Earth's oceans. But Jupiter's moons, despite their number and despite including several that are planet-sized, are gravitationally insignificant compared to their primary. This dominance is typical for gas giants. Unlike the inner solar system, where planets and moons have more comparable mass ratios, the outer solar system is defined by enormous planets, attended by relatively tiny satellites. It's a hierarchical structure where the planet is undisputed master, the moon's mere attendants. And yet, despite their negligible mass compared to Jupiter, these moons are fascinating in their own right. Europa's ocean might harbor life. Io's volcanism teaches us about tidal heating. Ganymede's magnetic field reveals processes we don't fully understand. The irregular moons are time capsules from the early solar system. Mass doesn't determine importance or interest. These worlds matter because of what they are, not how much they weigh. Jupiter's system is a reminder that significance isn't always about size or mass. The smallest components of a system can be the most interesting, the most complex, the most relevant to questions we care about. As you drift off, tiny compared to Earth, Earth tiny compared to Jupiter, Jupiter tiny compared to the Sun, remember that scale is just one dimension. Complexity, beauty, meaning, these exist at every scale, independent of mass. Jupiter has rings, though they're much fainter than Saturn's famous ring system. Jupiter's rings are composed mainly of dust, tiny particles knocked off the inner moons by micrometeorite impacts. When a small meteoroid strikes one of these moons, it excavates material, and some of that material escapes the moon's weak gravity, going into orbit around Jupiter and contributing to the ring. These inner moons, Metis, Adrastea, Amalthea, and Thebe, are both sources and sculptors of the rings. They provide the material through impacts, but they also gravitationally shape the ring structure. The rings aren't uniform. They have distinct components aligned with the orbits of these moons. The main ring corresponds to Metis and Adrastea's orbits. The gossamer rings extend outward, associated with Amalthea and Thebe. The moons act as what astronomers call shepherd moons, though that term is more commonly used for Saturn's moons. Their gravity constrains the ring particles, preventing them from spreading too far. Particles that drift too close to a moon might be absorbed or ejected from the system entirely. The result is that the rings maintain a structure related to the moon's orbits. Jupiter's rings are temporary on geological timescales. The dust particles are constantly being lost. Some fall into Jupiter's atmosphere due to drag. Others are pushed outward by radiation, pressure, and eventually escape the system. The rings only persist because they're constantly replenished by new impacts on the inner moons. If the moons weren't there, the rings would dissipate relatively quickly, perhaps in thousands or millions of years. It's a cycle. Impacts create rings. Rings fade. More impacts replenish them. The moons are slowly being eroded by this process, losing material grain by grain. Over billions of years, they're shrinking imperceptibly, sacrificing themselves to maintain the rings. Everything is temporary. Everything erodes. As you settle into sleep, Jupiter's rings shimmer faintly, dust particles catching sunlight, fed by moons that are themselves doomed to eventual erosion. All of it transient, beautiful, because it won't last forever. Let's return to Europa one more time, because it deserves it. This small moon, smaller than Earth's moon, might contain more water than our entire planet. All our oceans, all our ice caps, all our groundwater combined. Europa's ocean is estimated to be 40 to 100 miles deep, surrounding the entire moon. For comparison, Earth's oceans average about 2.3 miles deep. Europa's ocean is deeper, and it's global, uninterrupted by continents. And yet, when we look at Europa's surface, we see relatively few impact craters. Craters are the universal clock of planetary geology. The more craters, the older the surface. Bodies with ancient surfaces, like Callisto, are saturated with craters. Bodies with young surfaces, like Io or Europa, have few craters because geological activity erases them. Europa's relative lack of craters tells us its surface is young, probably only tens of millions of years old. This is recent on geological timescales. It means Europa's surface has been renewed within the time frame that includes the rise of mammals on Earth, the breakup of Pangaea, the most recent ice ages. Something is resurfacing Europa, erasing old craters and creating fresh ice. That something is probably related to the ocean. Perhaps the ice shell is thin enough in places that the ocean can reach the surface, flooding areas and creating new ice. Perhaps tectonic activity, the fracturing and movement of ice plates, buries old terrain under fresh material. Or perhaps impacts themselves puncture the ice, allowing water to well up and refreeze, erasing the very craters that created the holes. This youth suggests activity, and activity suggests energy. Energy suggests the potential for complex chemistry. Chemistry suggests, well, we don't know. But the possibility exists that Europa's ocean might be habitable, that life, probably microbial, probably simple, could exist in that dark sea. We're decades away from knowing. Future missions will orbit, will land, will drill, or melt through the ice. Until then, Europa keeps its secrets, a world of water beneath a fractured shell, young and active, holding mysteries that we're only beginning to unravel. As you drift off, Europa orbits, its ice cracking and healing, its ocean hidden, waiting. Jupiter's gravitational influence extends far beyond its moons. The planet acts as a kind of cosmic shield, protecting the inner solar system, including Earth, from some impacts. When comets from the outer solar system or asteroids from the asteroid belt approach the inner planets, they sometimes encounter Jupiter first. Jupiter's enormous gravity can alter their trajectories, deflecting them away from Earth-crossing orbits, or even capturing them entirely. This shielding effect isn't perfect. Jupiter can also redirect objects toward Earth rather than away. The gravitational interactions are complex, and whether an object is deflected inward or outward depends on the specifics of the encounter, the object's trajectory, speed, and timing. But on balance, many scientists believe Jupiter has reduced the impact rate on Earth throughout history. This matters for life. Earth's history includes several mass extinctions caused by asteroid or comet impacts. The most famous is the Chicxulub impact 66 million years ago that contributed to the extinction of the dinosaurs. Without Jupiter, such impacts might have been more frequent, possibly preventing complex life from evolving or repeatedly setting back the development of intelligence. There's some debate about how significant this shielding effect is. Computer simulations give different results depending on assumptions. Some models suggest Jupiter reduces Earth's impact rate by a factor of 1,000. Others suggest the effect is more modest, or even that Jupiter might increase impacts under certain conditions. The truth is probably somewhere in the middle. Jupiter provides some protection, but isn't a perfect shield. Still, it's intriguing to think that our existence might be partly thanks to Jupiter's gravitational dominance, that the giant planet's presence allowed Earth to remain relatively stable for billions of years, giving life time to evolve complexity. We might owe our existence in some indirect way to Jupiter's mass and position. As you rest safely, Jupiter continues its ancient orbit, deflecting objects, reshaping trajectories, its gravity reaching across millions of miles to influence what arrives in Earth's neighborhood. A distant guardian, indifferent to our fate, yet perhaps responsible for making our world a safer place. Between Mars and Jupiter lies the asteroid belt, a region filled with millions of rocky bodies ranging from tiny pebbles to objects hundreds of miles across. In early theories of the solar system, some astronomers thought the asteroid belt might be the remains of an exploded planet, debris from a catastrophe that shattered a world that once orbited there. We now know that's not what happened. The asteroid belt never was a planet. It's a planet that never formed, prevented from coalescing by Jupiter's gravitational influence. In the early solar system, when planets were forming from the protoplanetary disk, the region between Mars and Jupiter should have accumulated enough material to form a planet. But Jupiter's presence stirred up the region, accelerating asteroids to high speeds. When objects collide at low speeds, they stick together, gradually building larger bodies through accretion. But at high speeds, collisions become destructive rather than constructive. Objects shatter instead of merging. Jupiter's gravity kept the asteroid belt stirred up, preventing the gentle collisions that would have built a planet. Instead, asteroids smashed into each other, fragmenting, creating more smaller pieces rather than fewer larger ones. The result is a graveyard of a planet that never was, hundreds of thousands of objects that would have been planetary building blocks, but were prevented from completing their assembly. The total mass of the asteroid belt is small, less than our moon. If you could gather all the asteroids together, they wouldn't make a planet. They'd make a modest moon, a fraction of Earth's mass. Jupiter's influence extends even now. Certain regions of the asteroid belt are nearly empty, the Kirkwood Gaps, named after the astronomer who identified them. These are orbital distances where an asteroid would complete a simple fractional ratio of orbits compared to Jupiter, 2:1, 3:1, 5.2. At these resonances, Jupiter's repeated gravitational tugs add up over time, eventually ejecting asteroids from those orbits. The gaps are scars, empty zones carved by mathematical inevitability. As you drift off, the asteroid belt remains scattered, prevented from unifying, each rock a fragment of what might have been. Jupiter's gravity ensures they'll never combine, that the belt will remain a belt, a border region between the inner rocky worlds and the outer giants, forever incomplete. Not all objects that encounter Jupiter are deflected or captured. Some are accelerated, their velocities increased by gravitational assists. Slingshot maneuvers where the object steals a tiny amount of Jupiter's orbital energy. For small objects like comets, this can be dramatic. A comet that approaches Jupiter at the right angle can be accelerated to speeds exceeding the sun's escape velocity, fast enough to leave the solar system entirely. These ejected comets are now traveling through interstellar space, moving between stars. They'll never return to the sun. Barring incredibly unlikely encounters with other stars or their planets, they'll coast through the galaxy forever. Ambassadors from our solar system carrying ice and dust from the ancient solar nebula. How many such objects has Jupiter ejected? We don't know precisely, but models suggest it could be billions over the solar system's history. Every million years, hundreds or thousands of comets might be flung away by gravitational interactions with Jupiter. Over 4.5 billion years, that adds up to an enormous diaspora, a population of exiles wandering the galaxy. Some of these objects might eventually enter other star systems, becoming interstellar visitors like Oumuamua, the strange elongated object that passed through our solar system in 2017 and sparked speculation about its origin. Perhaps Oumuamua was ejected from another planetary system by that system's equivalent of Jupiter, and now our comets are visiting other systems in turn, a slow exchange of debris between stars. It's poetic in a way, Jupiter as an agent of exile, casting objects away, sending them on journeys that will last millions or billions of years. Some of these comets might outlast the sun itself, still traveling through the galaxy long after our star has swelled into a red giant and faded to a white dwarf. They'll be fossils of the early solar system, preserved in the cold of space, carrying water and organic molecules that formed around our sun to destinations unknown. As you rest, these exiles continue their journeys, billions of miles away and getting farther every second, lonely travelers in the dark between stars. Jupiter's gravitational influence creates stable points in space called Lagrange points, locations where the gravity of Jupiter and the Sun balance. In such a way that objects can remain in stable orbits, there are 5 such points, but 2 of them, L4 and L5, located 60 degrees ahead of and behind Jupiter in its orbit, are particularly stable and have accumulated populations of asteroids called Trojans. These Trojans are named after characters from the Trojan War in Homer's Iliad. The asteroids at the L4 point are mostly named after Greek heroes, while those at L5 are mostly named after Trojan defenders. There are thousands of known Trojans, and likely many more too small to detect. They're essentially hitchhikers, traveling along with Jupiter, maintaining their relative positions despite orbiting the Sun. The L4 and L5 points are stable because of the geometry and mathematics of orbital mechanics. An object placed there experiences gravitational forces from both the Sun and Jupiter that keep it locked in position relative to Jupiter. Small perturbations, gravitational tugs from other planets, or the asteroid drifting slightly off position are self-correcting. The object oscillates gently around the Lagrange point but doesn't escape. This same principle works for other planet-sun systems. Earth has Trojan asteroids at its L4 and L5 points, though fewer than Jupiter. Mars has some. Neptune has a large population. The Lagrange points are cosmic parking lots, stable locations where objects can remain for billions of years with minimal perturbation. Why does this matter? For space exploration, Lagrange points offer strategic locations for spacecraft, places where fuel expenditure for station keeping is minimal. The James Webb Space Telescope orbits Earth's L2 point. For understanding the solar system's history, Trojan asteroids are time capsules, preserved in stable orbits since the early solar system. As you drift towards sleep, thousands of asteroids drift in Jupiter's orbit, always ahead or behind, never catching up, never falling back, held in gravitational equilibrium, passengers on an eternal journey around the sun, companions to the giant but never touching, forever separated by 60 degrees of orbital arc, close but infinitely far. the planets might not have formed where they are now. Emerging evidence suggests the outer planets, Jupiter, Saturn, Uranus, Neptune, didn't form in their current positions, but migrated over time, moving inward or outward due to gravitational interactions with the disk of gas and dust that filled the early solar system. Jupiter, according to one model called the Grand Tack, might have migrated inward toward the Sun during the first few million years after formation, traveling perhaps as close as Mars's current orbit. Then, as Saturn formed and caught up to Jupiter, the two planets became locked in resonance, and their combined gravitational influence reversed Jupiter's migration, pulling it back outward to roughly its present position. This inward then outward journey would have had profound consequences. As Jupiter moved, it would have scattered planetesimals, the building blocks of planets, throughout the inner solar system. Some would have been ejected entirely. Others would have been pushed into the inner regions, possibly delivering water and organic materials to the young Earth. Still others might have collided with forming planets, adding or removing mass. This migration might explain why Mars is so small, if Jupiter's inward migration stirred up and scattered the material that should have built Mars, preventing it from growing larger. It might explain the asteroid belt's low mass. It might explain aspects of Earth's composition. Other models, like the Nice model, named after the French city where it was developed, focus on later migrations during a period called the Late Heavy Bombardment, roughly 4 billion years ago. In this scenario, Neptune and Uranus migrated outward, destabilizing the outer solar system and sending a shower of comets and asteroids into the inner solar system, causing the spike in impact craters we see on the Moon and other bodies. These are models, not certainties, but they suggest the solar system's current architecture isn't original, that planets moved, that Jupiter might have wandered close enough to threaten the inner planets before retreating. As you drift off, imagine Jupiter's ancient migration, a giant planet moving through a dusty disk, reshaping orbits, scattering debris, creating the solar system we inherited billions of years later. The planets don't orbit in isolation. They influence each other gravitationally, creating subtle perturbations in each other's paths. Most of the time, these effects are small, averaged out over time. But periodically, when planets align in particular configurations, their combined gravitational influence becomes more significant. Jupiter and Saturn, the two most massive planets, align roughly every 20 years, a configuration called a Great Conjunction, when they appear close together in Earth's sky. During these alignments, their gravitational pulls on the inner planets add up rather than cancel out. Earth experiences a slight tug, a gentle perturbation in its orbit. The effect is tiny. Earth's orbit shifts by perhaps a few hundred miles, negligible compared to Earth's 93 million mile distance from the Sun. But it's measurable with modern instruments. Astronomers can detect these perturbations in Earth's motion, in the timing of planetary transits, in the precise positions of planets against the background stars. Ancient astrologers marked these great conjunctions as significant events, believing they portended major changes in human affairs. They were right that something significant was happening, just gravitationally rather than mystically. The alignments do create real physical effects, though not the ones medieval astrologers imagined. These planetary interactions are part of why predicting planet positions far into the future becomes difficult. The solar system is deterministic, governed by Newton's laws and Einstein's refinements, but it's also chaotic in the mathematical sense. Small perturbations accumulate over time in ways that make long-term predictions uncertain. We can calculate where Jupiter will be 1,000 years from now with good accuracy. 10,000 years, less certain. 1,000,000 years? The uncertainties compound until predictions become unreliable. The solar system is stable on billion-year timescales. The planets won't suddenly eject or collide, but their precise positions far in the future are fundamentally unpredictable due to this chaos. As you rest, Earth experiences Jupiter and Saturn's gentle tugs. Barely perceptible shifts in our orbit, reminders that we're part of a gravitational dance involving all the planets, all influencing each other across vast distances. Comets that venture into the inner solar system from the distant Oort cloud or Kuiper belt are already traveling quickly. They've fallen inward from the outer reaches, accelerated by the sun's gravity. But if a comet's trajectory takes it near Jupiter, the giant planet's gravity can accelerate it further, adding velocity through gravitational interaction. This process, called a gravitational slingshot, works because the comet steals a tiny amount of Jupiter's orbital momentum. Jupiter is so massive that the effect on Jupiter is immeasurably small. But for a comet, a relatively tiny object, the velocity change can be dramatic. A comet approaching at, say, 30,000 miles per hour might leave the encounter traveling at 50,000 or 60,000 miles per hour. If the velocity increase is large enough, the comet can exceed the sun's escape velocity, about 26 miles per second from Jupiter's orbital distance. At that speed, the comet is no longer bound to the solar system. It will coast outward forever, eventually entering interstellar space. These comets become wanderers, traveling between stars, carrying ice and organic molecules from our solar system into the galaxy. This process has been occurring for billions of years. Jupiter has ejected countless comets, gradually cleaning out the inner region of long-period comets that might otherwise threaten Earth. It's another aspect of Jupiter's role as gravitational architect, reshaping the orbits of smaller bodies through countless close encounters. We use this same technique for spacecraft. Voyager 1 and 2 both used Jupiter's gravity to accelerate toward their outer solar system destinations. The spacecraft approached Jupiter, swung around the planet, and left with significantly increased velocity, enough to reach Saturn, Uranus, Neptune, and eventually escape the solar system entirely. We're hitchhikers on Jupiter's gravity, borrowing momentum for our exploration. As you drift toward sleep, comets continue their journeys. Some bound to the sun, others accelerated past escape velocity by encounters with Jupiter, beginning lonely voyages into the interstellar medium where they'll travel for millions of years through darkness, monuments to gravitational mechanics, ice and dust from the early solar system spreading slowly through the galaxy. If you plotted the distribution of asteroids in the asteroid belt by their distance from the sun, you'd notice something strange. Certain distances have very few asteroids. These are the Kirkwood Gaps, named after Daniel Kirkwood, who identified them in the 1860s. They're empty zones carved into the asteroid belt by Jupiter's gravitational influence through orbital resonance. Resonance occurs when the orbital period of an asteroid is a simple fraction of Jupiter's orbital period, 2131 5.273, and so on. An asteroid at the 2-1 resonance completes exactly 2 orbits for every 1 orbit of Jupiter. This means Jupiter and the asteroid align at the same point in their orbits every 2 asteroid years, and Jupiter's gravitational tug occurs at the same point in the asteroid's orbit repeatedly. These repeated tugs, over millions of years, add up. They gradually increase the eccentricity of the asteroid's orbit, making it more elongated, until eventually the asteroid's orbit becomes so eccentric that it crosses the orbit of Mars or even Earth. At that point, the asteroid is likely to encounter one of these planets, and the encounter either ejects it from the resonance or removes it from the asteroid belt entirely. The result is that resonant locations become depleted over time. Asteroids that happen to find themselves at these distances are gradually removed, leaving gaps. The gaps aren't completely empty. Asteroids can still pass through them, but they have significantly fewer permanent residents than neighboring regions. These gaps are examples of gravitational sculpting, Jupiter shaping the asteroid belt's structure through patient, persistent influence operating over geological time. The asteroid belt isn't a random distribution of rocks. It's organized by resonances, patterned by mathematics, a structure imposed by Jupiter's gravity even across hundreds of millions of miles. As you close your eyes, the Kirkwood gaps remain empty, swept clean by resonances, mathematical regions where asteroids cannot stably exist. Jupiter's influence reaches across the solar system, creating order in unexpected places, carving patterns into populations of rocks through nothing but gravity and time, invisible hands arranging the asteroid belt into its current configuration. Mars is smaller than it should be. Based on models of planet formation and the distribution of material in the early solar system, Mars should be more massive, perhaps 2 or 3 times its current size, closer to Earth's mass. But Mars is only about 1/10 Earth's mass, barely larger than Mercury. What happened? One possibility is Jupiter. If Jupiter formed quickly and migrated inward during its early history, as the Grand Tack hypothesis suggests, it would have passed through or near the region where Mars was forming. Jupiter's gravity would have stirred up the planetesimals in that region, accelerating them to high velocities and scattering them throughout the inner solar system or ejecting them entirely. With the building materials depleted or scattered, Mars couldn't grow larger. It became a stranded planetary embryo, a planet that never finished forming because its feeding zone was emptied by Jupiter's passage. The Mars we see today is essentially what existed before Jupiter's migration, frozen in size because there was nothing left to accrete. This would also explain why Mars's composition is slightly different from Earth's. Perhaps Mars formed from material in a different region and never accumulated the additional material that would have homogenized its composition. It would explain the asteroid belt's low mass. Jupiter scattered most of the material that should have been there. If this is true, then Mars's small size and potentially Mars's inability to maintain a thick atmosphere and surface water over geological time is ultimately Jupiter's fault. A larger Mars might have retained its atmosphere, might still have liquid water on its surface, might be more Earth-like. Jupiter's gravitational influence might have determined whether Mars would be habitable. As you rest, Mars orbits, small and cold, a world that might have been different if Jupiter hadn't passed through during the solar system's youth. Jupiter's ancient migration shaped not just its own destiny, but the destinies of other worlds, determining which planets would be large and which would remain small, which might host life and which would remain barren. Gravity shapes not just orbits, but possibilities. Look at the moon through a telescope, and you'll see its heavily cratered surface, scars from billions of years of impacts. Most of these craters formed during a period called the Late Heavy bombardment, roughly 4.1 to 3.8 billion years ago, when the impact rate throughout the inner solar system suddenly increased. The Moon, Earth, Mars, Mercury, all were bombarded with asteroids and comets during this relatively brief period. What caused this spike in impacts? The NEISS model offers an explanation. The outer planets migrated, and their migration destabilized the outer solar system. Jupiter and Saturn, initially in resonance, eventually broke out of that resonance and shifted to their current orbital configuration. This shift disturbed Neptune and Uranus, pushing them outward. As Neptune migrated outward, it plowed through the outer solar system's population of planetesimals, icy bodies left over from planet formation. These objects were scattered chaotically. Some were ejected from the solar system entirely. Others were thrown inward, creating a sudden influx of comets and asteroids into the inner solar system. For a few 100 million years, Earth and the Moon experienced intense bombardment. Then, as the outer planets settled into their current orbits, and the remaining planetesimals were either ejected or captured, the bombardment ended. The impact rate dropped to the low, steady rate we observe today. This bombardment had consequences for Earth. Some scientists think it might have reset Earth's surface, sterilizing the planet if life had already emerged. Others think the impactors delivered water and organic molecules, providing the ingredients for life. The bombardment might have been both destroyer and creator, clearing away early attempts at life while simultaneously providing the materials for new beginnings. The exact timing is significant. Life on Earth seems to have emerged shortly after the late heavy bombardment ended. The oldest fossils date to about 3.5 billion years ago. Perhaps life couldn't establish itself while the bombardment was ongoing. Once it ended, life seized the opportunity. As you drift off, imagine that ancient rain of rocks, Jupiter's migration setting in motion events that would bombard Earth and perhaps create the conditions necessary for your eventual existence billions of years later. For most of human history, Jupiter was a point of light, a wandering star we could observe only from Earth's distance. Then in the 1970s, we began visiting. Pioneer 10, launched in March 1972, became the first spacecraft to reach Jupiter in December 1973. It returned the first close-up images of the planet, revealing details invisible from Earth. The complex structure of cloud bands, the turbulent boundary regions between zones and belts, the true nature of the Great Red Spot. Pioneer 10's flyby was brief. The spacecraft raced past Jupiter at high speed, using the planet's gravity to accelerate toward the outer solar system. Its twin, Pioneer 11, followed a year later, providing more data and images. Then came Voyager 1 and 2 in 1979, with more sophisticated instruments and cameras. The Voyager images were stunning. Color photographs showing Jupiter's atmospheric complexity, time-lapse sequences revealing the dynamics of storms, discoveries of volcanic activity on Io, and possible oceans beneath Europa's ice. Each mission revealed something unexpected. Voyager discovered Jupiter's faint ring system, something no one had predicted. It observed Io's volcanism in real time, catching eruptions in the act. The data revolutionized our understanding, transforming Jupiter from a distant object to a dynamic, comprehensible world. Later missions, Ulysses, 1992, Cassini, 2000, New Horizons, 2007, flew past Jupiter on their way to other destinations, adding to our knowledge. But the most transformative mission since Voyager has been Juno, which entered orbit around Jupiter in 2016 and has been studying the planet in detail ever since. Each spacecraft carried human-built instruments, cameras, spectrometers, magnetometers, billions of miles to study a world no human could visit. These robots are our emissaries, our eyes and hands extending across the solar system, gathering data and sending it home at the speed of light. As you rest, Juno continues orbiting, skimming close to Jupiter's cloud tops every 53 days, measuring magnetic fields and gravity, peering through the clouds to see what lies beneath. A tireless explorer in one of the solar system's most extreme environments. While flybys provide snapshots, orbiting missions provide sustained observation. Galileo, launched in 1989, arrived at Jupiter in 1995 and became the first spacecraft to orbit the planet. Over 8 years, Galileo completed 35 orbits, each one carefully designed to study different aspects of Jupiter's system. Close flybys of the Galilean moons, observations of Jupiter's atmosphere, measurements of the magnetosphere. Galileo discovered that Ganymede has a magnetic field. It found evidence for subsurface oceans on Europa, Ganymede, and Callisto. It observed Io's volcanism in detail, documenting changes between different observation periods. It watched as comet Shoemaker-Levy 9 crashed into Jupiter in 1994, providing a front-row seat to one of the most dramatic events in solar system observation. The mission faced challenges. Galileo's high-gain antenna failed to deploy properly, reducing its data transmission rate by a factor of hundreds. Engineers had to develop new compression techniques and carefully prioritize what data to send. Despite this handicap, Galileo returned valuable science throughout its mission. When Galileo's mission ended in 2003, controllers faced a choice. Leave the spacecraft in orbit where it might eventually crash into Europa, potentially contaminating that moon's potentially habitable ocean, or deliberately destroy it. They chose destruction. Galileo was commanded to plunge into Jupiter's atmosphere at high speed, burning up and vaporizing, ensuring it wouldn't contaminate any of the moons. This deliberate sacrifice, destroying a spacecraft to protect potential life elsewhere, reflects our growing awareness of planetary protection, the ethical responsibility to avoid contaminating other worlds with Earth life. Galileo's death was purposeful, a final act of responsibility. As you close your eyes, Galileo's atoms have long since been incorporated into Jupiter's atmosphere, the spacecraft destroyed, but its legacy preserved in the data it returned. Knowledge that outlives the machine that gathered it. Galileo didn't just orbit Jupiter. It also carried a probe designed to descend into the atmosphere. On December 7, 1995, this probe separated from the orbiter and plunged into Jupiter's atmosphere at over 100,000 miles per hour. The entry was violent. The probe experienced deceleration of 230 times Earth's gravity, temperatures of 28,000 degrees Fahrenheit, enough to vaporize most materials. But the probe's heat shield survived, protecting the instruments inside. After slowing enough, the probe deployed a parachute and began descending, measuring temperature, pressure, composition, wind speed as it fell. For 58 minutes, it transmitted data back to the Galileo orbiter overhead, which recorded the signal and later relayed it to Earth. The probe descended about 100 miles, experiencing pressures up to 23 times Earth's atmospheric pressure at sea level, and temperatures exceeding 300 degrees Fahrenheit. Then the probe stopped transmitting. The heat and pressure became too much. The electronics failed. The structure collapsed. The probe was crushed and eventually vaporized, its atoms becoming part of Jupiter's atmosphere. But in those 58 minutes, it gathered invaluable data, direct measurements of Jupiter's atmosphere, the first in situ sampling of a gas giant's environment. The probe found that Jupiter's atmosphere at that location was surprisingly dry, with less water than expected. This was puzzling until scientists realized the probe had descended through an unusually dry region, like landing in a desert and concluding Earth is dry. The probe also measured unexpectedly strong winds at depth, suggesting Jupiter's atmospheric circulation extends far below the visible cloud tops. This was the deepest any human-made object has penetrated into Jupiter. No spacecraft since has attempted a similar descent. The probe's brief life was violent, intense, and scientifically productive, a complete mission in less than an hour. As you drift towards sleep, that probe's atoms remain part of Jupiter, dispersed into the vast atmosphere, mixed with hydrogen and helium, forever part of the giant planet. Before Voyager, no one was certain whether Jupiter had rings. Saturn's magnificent rings were obvious, but Jupiter showed no signs of similar structures in Earth-based observations. When Voyager 1 approached Jupiter, mission planners included a speculative observation, pointing the camera back toward the Sun with Jupiter eclipsing it, hoping to catch any faint, forward scattered light from unseen rings. The gamble paid off. Voyager 1's images revealed a faint ring system, much dimmer than Saturn's but definitely present. Voyager 2 confirmed the discovery and provided better images. Jupiter's rings consist mainly of dust-sized particles, dark and reddish, nearly transparent. They're so faint that they can only be seen when backlit or observed from specific angles. We now know the rings are constantly replenished by micrometeorite impacts on Jupiter's inner moons. Each impact ejects material, some of which goes into orbit around Jupiter, contributing to the ring. Without this constant replenishment, the rings would dissipate in thousands of years. They're maintained by ongoing erosion of the moons, a cycle of destruction and creation. The discovery reminds us that space exploration involves surprises. We go looking for expected features and find the unexpected. We answer questions and generate new ones. Voyager went to Jupiter to study the planet and its moons, but it also discovered rings, found active volcanism on Io, revealed Europa's cracked ice, none of which were primary mission objectives. This is why exploration matters, not just to confirm what we expect, but to discover what we don't. The universe is under no obligation to match our predictions. As you close your eyes, Jupiter's faint rings circle the planet, nearly invisible, composed of dust knocked off dying moons, a feature discovered by accident, existing quietly in the shadow of the giant, unseen from Earth but undeniably real. Juno represents a new generation of Jupiter exploration. Unlike previous missions that stayed relatively distant or made brief flybys, Juno enters a highly elliptical orbit that brings it skimming just 3,000 miles above Jupiter's cloud tops, closer than any previous mission. At this distance, Juno experiences intense radiation, bathed in particle bombardment that gradually degrades its electronics despite heavy shielding. Juno's orbit is designed to avoid the worst radiation for most of each orbit, spending most of its time far from Jupiter and diving close only briefly. Each close approach lasts a few hours, during which Juno's instruments work furiously, measuring Jupiter's gravity field, magnetic field, composition, and atmospheric structure. The gravity measurements have been particularly revealing by precisely tracking how Jupiter's gravity tugs Juno during each close pass. Scientists can infer how mass is distributed inside the planet. These measurements suggest Jupiter's core isn't a neat, solid sphere, but is fuzzy or diluted, perhaps dissolved into the surrounding metallic hydrogen, or mixed with it during a violent collision early in Jupiter's history. Juno has also studied Jupiter's polar regions in detail for the first time. Previous missions orbited Jupiter's equator, never seeing the poles close up. Juno's polar orbit revealed those strange, geometric arrangements of storms, octagons and pentagons that cluster around each pole. It discovered that Jupiter's magnetic field is more complex and irregular than expected, with patches of reversed polarity. The mission has been extended multiple times, with Juno continuing to orbit and gather data years beyond its original planned lifetime. Radiation damage accumulates. Eventually, Juno's electronics will fail. But for now, it continues working, revolutionizing our understanding with each orbit. As you drift off, Juno races toward Jupiter again, crossing millions of miles in weeks, preparing for another close encounter, instruments ready to measure and record, gathering data that will reshape what we know about how giant planets work. Some missions visit Jupiter not as a destination but as a stepping stone. New Horizons, launched in 2006 to study Pluto and the Kuiper Belt, needed to reach the outer solar system quickly. Flying directly would have taken decades. Instead, mission planners used Jupiter as a gravitational accelerator. New Horizons approached Jupiter in early 2007, swung around the planet, and emerged with significantly increased velocity, enough to reach Pluto by 2015 rather than the 2030s or 2040s. During its brief Jupiter flyby, New Horizons wasn't idle. It carried cameras and instruments, and though its primary mission lay billions of miles ahead, it gathered valuable Jupiter data during its passage. The spacecraft studied Jupiter's ring system, observed Eo's volcanism, tracked atmospheric storms, and measured magnetosphere properties. It captured time-lapse videos showing the Great Red Spot's rotation and cloud dynamics over several days. New Horizons also tested its instruments during the Jupiter encounter, ensuring everything worked properly before the long cruise to Pluto. The flyby was a rehearsal for the Pluto encounter 8 years later, a chance to practice targeting, timing, and data collection under real mission conditions. The gravitational assist worked perfectly. New Horizons stole a tiny amount of Jupiter's orbital momentum, an amount so small that Jupiter's orbit didn't measurably change, and converted it into additional velocity. The spacecraft left Jupiter traveling at about 47,000 miles per hour relative to the Sun, fast enough to reach Pluto in less than a decade. This technique has been used for many missions. Voyager, Cassini, Galileo all used Jupiter gravity assists to reach their destinations. It's elegant, using planetary motion to propel spacecraft, borrowing momentum from worlds that have been orbiting for billions of years, hitchhiking on gravity. As you rest, New Horizons continues its journey beyond Pluto, now in the Kuiper Belt, coasting on velocity borrowed from Jupiter over 15 years ago, still moving through space on momentum stolen from the giant. While spacecraft visit Jupiter briefly, the Hubble Space Telescope provides continuous monitoring from Earth orbit. Since its launch in 1990, Hubble has observed Jupiter regularly, creating a long-term record of atmospheric changes. These observations show how storms evolve, how the Great Red Spot shrinks, how new storms form and existing ones merge or dissipate. Hubble's images have documented changes that occur on human timescales, shifts in cloud band colors, alterations in storm sizes, the birth of new atmospheric features. By comparing images taken years or decades apart, astronomers can track long-term trends and understand Jupiter's atmospheric variability. Hubble also watches for impacts. After comet Shoemaker-Levy 9's spectacular collision with Jupiter in 1994, astronomers realized that impacts on Jupiter might be more common than expected. Since then, Hubble and amateur astronomers have detected several smaller impacts. Asteroids or comets striking Jupiter, creating temporary dark scars in the atmosphere that fade over weeks or months. These impact observations are valuable because they tell us about the population of small objects in the outer solar system. Objects too small to detect directly, but revealed when they collide with Jupiter. The impact rate helps astronomers estimate how many potentially hazardous objects exist in the solar system and what threat they might pose to Earth. Hubble has also detected Europa's water vapor plumes, studied auroras on Jupiter and its moons, observed how Jupiter's atmosphere responds to seasonal changes and internal dynamics. It's a patient observer, returning to Jupiter again and again, building a multi-decade record that no single spacecraft mission could match. The partnership between spacecraft missions and telescope observations is powerful. Spacecraft provide close-up detail and direct measurements. Telescopes provide context and long-term monitoring. Together, they create a comprehensive picture of Jupiter's nature and behavior. As you drift off, Hubble orbits Earth, its instruments occasionally turning toward Jupiter, gathering photons that left the giant planet over 40 minutes ago, adding to humanity's growing archive of knowledge about the King of Planets. In July 1994, the astronomical community witnessed something unprecedented: a comet colliding with a planet. Comet Shoemaker-Levy 9 had fragmented during a previous close pass of Jupiter, breaking into more than 20 pieces. These fragments, strung out like pearls on a necklace, were on a collision course with Jupiter. Over the course of a week, the fragments struck Jupiter's atmosphere on the far side, out of view from Earth. But as Jupiter rotated, the impact sites came into view, revealing dark scars in the atmosphere, bruises larger than Earth itself. The impacts released staggering energy. The largest single impact released energy equivalent to 6 million megatons of TNT, roughly 600 times the explosive power of the entire world's nuclear arsenal. The impacts taught us about Jupiter's atmosphere, how it responds to sudden energy input, how material gets distributed by winds, how quickly the scars fade. They also taught us about impact dynamics. What happens when a comet fragment strikes at tens of kilometers per second? How the energy is distributed between the fragment's kinetic energy and chemical energy from the explosion. Perhaps most importantly, the impacts reminded us that collisions still happen in the solar system. Jupiter gets hit regularly, not always by objects as large as Shoemaker-Levy 9, but small impacts occur every few years. If Earth were as large as Jupiter, with Jupiter's gravitational influence, we'd be struck far more frequently than we are. The event was observed by every available telescope: Hubble, ground-based observatories, the Galileo spacecraft then approaching Jupiter. Amateur astronomers watched through backyard telescopes. For a week, humanity collectively observed a cosmic collision, witnessing the violent side of planetary dynamics. The scars faded over months, absorbed and dispersed by Jupiter's atmosphere, but the images remain, archived proof that space can be violent, that impacts aren't just relics of the ancient past, but ongoing processes. As you rest safely, Jupiter continues absorbing impacts, its massive gravity attracting debris, occasionally intercepting objects that might otherwise have wandered through the inner solar system toward Earth. Jupiter's auroras emit not just visible and ultraviolet light, but also X-rays, high-energy electromagnetic radiation normally associated with extremely hot objects like the sun's corona or exotic phenomena like black holes. For decades, scientists couldn't explain how Jupiter's auroras produced X-rays. The temperatures in Jupiter's aurora aren't hot enough for thermal X-ray emission, so some other process must be at work. Recent research combining observations from Earth-based telescopes, Juno spacecraft data, and computer modeling finally cracked the puzzle. The X-rays come from heavy ions, charged atoms of sulfur and oxygen stripped from Io's volcanic eruptions, surfing electromagnetic waves toward Jupiter's poles. Here's how it works. Jupiter's rapid rotation creates powerful electric and magnetic fields. These fields generate waves, oscillations in the electromagnetic field that ripple through the magnetosphere. Heavy ions trapped in the magnetosphere can be caught by these waves and accelerated, riding the wave like a surfer rides ocean swells. As the ions surf toward the poles, they gain enormous energy. When they finally crash into Jupiter's upper atmosphere, they release that energy as X-rays. It's a beautiful piece of physics. Electromagnetic waves accelerating particles to high energies. Particles releasing that energy as high-frequency radiation. The process connects Io's volcanism to Jupiter's magnetic field, to the atmosphere to X-ray emissions, linking multiple components of the Jovian system in a complex chain of cause and effect. Understanding this mechanism matters beyond Jupiter. Similar processes might occur around other planets, around pulsars, around black holes. Anywhere you have strong magnetic fields, trapped particles, and electromagnetic waves. Jupiter serves as an accessible laboratory for studying plasma physics phenomena that occur throughout the universe. As you drift towards sleep, Jupiter's poles glow with X-rays, invisible to human eyes but bright in X-ray telescopes. Ions torn from iosurf electromagnetic waves across millions of miles, accelerating to incredible energies before crashing into the atmosphere, their violence creating beauty, their collisions producing light at wavelengths that would harm any life exposed to them. Physics plays out on a grand scale, indifferent to observers, creating phenomena we're only now beginning to understand. The exploration of Jupiter continues. The European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, launched in April 2023 and is now en route to Jupiter. It won't arrive until 2031, requiring 8 years and multiple gravity assists from Earth and Venus to reach the outer solar system. But when it arrives, JUICE will conduct the most comprehensive study yet of Jupiter's icy moons. The mission will focus particularly on Ganymede, Europa, and Callisto, the 3 Galilean moons most likely to have subsurface oceans. JUICE will orbit Jupiter initially, making multiple flybys of these moons, studying their surfaces, measuring their magnetic fields, probing their interiors with radar and gravity measurements. Then, in a historic first, JUICE will enter orbit around Ganymede, the first time any spacecraft has orbited a moon other than Earth's moon. From Ganymede orbit, JUICE will study that moon in unprecedented detail. It will map the surface at high resolution, characterize the subsurface ocean, study the magnetic field's structure, and search for signs of geological activity. The mission will help answer fundamental questions. How thick is the ice? How deep is the ocean? What chemicals exist in it? Is the ocean connected to the rocky seafloor, where interesting chemistry might occur? JUICE will also study Jupiter itself, though that's a secondary objective. It will observe the atmosphere, map the magnetosphere, characterize the radiation environment. But the primary goal is understanding the icy moons, these small worlds that might harbor habitable environments, that might teach us about the potential for life in the outer solar system. 8 years from now, as JUICE arrives and begins its mission, our understanding of Jupiter's moons will transform again, just as it did with Voyager, Galileo, and Juno. Each mission reveals new mysteries while solving old ones, each answer generating new questions. As you drift off, JUICE continues its lonely voyage through space, crossing millions of miles, en route to a rendezvous 8 years hence, carrying instruments designed to peer beneath ice and discover what secrets Europa, Ganymede, and Callisto hold in their hidden oceans. For all we've learned about Jupiter, fundamental questions remain unanswered. How did Jupiter form? 2 main theories compete. The core accretion model suggests Jupiter formed like terrestrial planets, starting with a solid core of rock and ice that gradually accumulated mass until it grew large enough, perhaps 10 to 20 Earth masses, that its gravity could capture surrounding hydrogen and helium gas. The gas accumulated rapidly, building up Jupiter's massive atmosphere. The alternative is gravitational instability. In this model, a region of the protoplanetary disk became so dense that it collapsed directly under its own gravity, forming a gas giant without requiring a pre-existing solid core. The gas condensed, perhaps forming a core later as heavier elements sank toward the center, but the core wasn't the starting point. It was a consequence of formation, not the cause. Juno's measurements of Jupiter's interior, that fuzzy, diluted core, complicate both models. If core accretion is correct, why isn't the core more distinct? Perhaps a giant impact early in Jupiter's history stirred up the interior, mixing core material with the surrounding metallic hydrogen. Or perhaps the core partially dissolved over billions of years under extreme heat and pressure. If gravitational instability formed Jupiter, why does it have a core at all, however fuzzy? Maybe heavy elements naturally settled toward the center over time. Or maybe both processes occurred. Gravitational instability created a proto-Jupiter that then accreted additional material in a way resembling core accretion. We don't know. The answer matters because understanding how Jupiter formed helps us understand how planetary systems form generally. Exoplanet discoveries show that gas giants are common around other stars, but they exist in different configurations. Hot Jupiters orbiting close to their stars, eccentric giants on elongated orbits, systems unlike our own. Did they all form the same way? As you drift towards sleep, Jupiter holds its secrets, its interior structure and formation history, still partially mysterious despite decades of study. A reminder that even familiar objects can remain enigmatic, that understanding takes time and patience, and probably more missions yet to come. Jupiter's fuzzy core might have a violent explanation. Recent computer models suggest that during Jupiter's formation, it might have collided with and absorbed several planetary embryos, objects the size of Earth or Mars that were forming in the same region. These collisions would have been catastrophic, releasing enormous energy and stirring up Jupiter's interior. When a planet-sized object strikes Jupiter at tens of kilometers per second, it doesn't just bounce off or create a crater. It punches deep into the interior, its kinetic energy converted to heat and shock waves. The impactor's material, rock, metal, ice, mixes with Jupiter's metallic hydrogen and helium, distributing throughout a large volume rather than settling into a neat, distinct core. If Jupiter experienced several such giant impacts during its first 100 million years, the accumulated effect could explain why its core seems larger and more diffuse than expected. The core might not be a single cohesive object, but rather the combined remnants of multiple planetary bodies, mixed with Jupiter's original core material and partially dissolved or dispersed throughout the deep interior. This scenario makes Jupiter a graveyard of sorts, a giant planet whose interior contains the remains of other worlds that almost became planets themselves, but were instead consumed during the chaotic early solar system. Those vanished worlds' atoms now form part of Jupiter, their identities erased, their potential futures ended. It's sobering to imagine. Somewhere inside Jupiter might be the remains of a world that, if it had survived, might have become a rocky planet, might eventually have developed life, might have had its own story. Instead, it collided with Jupiter during the solar system's youth and ceased to exist as a separate entity. As you drift off, consider that Jupiter might be more complex than it appears. Not just hydrogen and helium and a core, but a composite made from multiple absorbed worlds, a giant built partly from the corpses of planets that failed to survive the early solar system's violence. We see Jupiter's storms from above, looking down at their tops, but we don't know how deep they extend. The Great Red Spot, those white ovals, the brown barges, are they deep features extending thousands of miles into the interior? Or are they shallow, confined to the upper layers of atmosphere? Juno's gravity measurements provide clues. By precisely measuring how Jupiter's mass is distributed, scientists can infer the depth of atmospheric features. Preliminary results suggest some features extend surprisingly deep, perhaps several hundred miles below the cloud tops, but other features seem shallower, confined to the upper atmosphere. The depth matters for understanding Jupiter's energy budget and circulation. If storms are shallow, they're probably driven mainly by solar heating and the temperature difference between different latitudes. If they're deep, they tap into Jupiter's internal heat, connecting the visible atmosphere to the churning metallic hydrogen ocean far below. The Great Red Spot probably extends deep. Its longevity and power suggest it's rooted in deeper atmospheric layers, perhaps reaching down to where pressures are tens or hundreds of times Earth's surface pressure. But smaller storms might be shallower, more transient features that form and dissipate in the upper atmosphere without significantly affecting deeper layers. Understanding storm depth also helps us model Jupiter's interior structure. Where does the atmosphere end and the interior begin? There's no sharp boundary, but there must be a transition zone where atmospheric circulation gives way to deeper, slower convection. Finding this boundary is one of Juno's goals, and the depth of storms provides clues. As you rest, those storms churn at various depths, some reaching far below what we see, others floating on the surface like cream on coffee. All of them part of a three-dimensional circulation system that spans thousands of miles vertically as well as horizontally. Jupiter's atmosphere isn't a thin shell, it's a volume, thick enough to contain entire worlds, with structure and dynamics at every level, from cloud tops to the metallic hydrogen ocean below. Jupiter occasionally produces brief, bright flashes in its upper atmosphere, transient luminous events that appear and disappear in seconds or milliseconds. They're not lightning, which occurs deeper in the atmosphere and has different characteristics. They're not impacts from meteors, which would look different and occur less frequently. So what are they? These events occur at high altitudes, above the main cloud layers, in Jupiter's stratosphere or even higher. They're bright enough to be detected from Earth or by spacecraft, but they're rare and unpredictable. Catching one requires either continuous monitoring or luck. Some might be electrical discharges similar to Earth's sprites or jets. Upward lightning that occurs above thunderstorms, reaching into the stratosphere. On Earth, these phenomena were only discovered in the 1990s because they're brief and occur above storms where they're difficult to observe. Jupiter might have similar features, but on a grander scale. Others might be chemical reactions, perhaps atmospheric molecules excited by high-energy particles from the magnetosphere, releasing energy as light when they de-excite, or perhaps meteors vaporizing in the upper atmosphere, though these would be small objects, nothing like Shoemaker-Levy 9's large fragments. The flashes remain mostly mysterious. They happen too quickly for detailed spectroscopic analysis with current instruments. They're too rare for systematic study. Each detection is an event, not a data set. Future missions might monitor Jupiter continuously, capturing these events in detail and finally determining their nature. It's humbling that even basic phenomena, bright flashes in an atmosphere we've studied for decades, remain unexplained. Jupiter continues surprising us, continues producing events we don't fully understand. As you close your eyes, Jupiter's upper atmosphere occasionally flickers with brief, mysterious flashes. Atmospheric ghosts that appear and vanish, phenomena awaiting explanation, reminders that even well-studied worlds hold secrets, that mystery persists even in the age of spacecraft and sophisticated instruments. The conditions inside Jupiter, pressures millions of times Earth's atmosphere, temperatures tens of thousands of degrees, strong magnetic and electric fields, are so extreme that matter behaves in ways impossible to replicate in terrestrial laboratories. The metallic hydrogen ocean is one example, but there might be others. Under extreme pressure, Molecules and atoms are forced so close together that their electron clouds overlap. Normal chemical bonds can't form. Instead, matter enters exotic states where quantum mechanical effects dominate. Electrons might become delocalized, shared among many atoms in ways that change the material's properties dramatically. There might be regions where hydrogen and helium mix in unusual ratios, creating alloys that don't exist anywhere else. There might be layers where different forms of hydrogen, molecular, metallic, perhaps even other phases we haven't imagined, coexist in equilibrium. The boundary regions between different layers might have unique properties, materials that exist only at specific combinations of pressure, temperature, and composition. Some of these exotic states might have strange properties: superfluidity, superconductivity, unusual optical or magnetic characteristics. They might behave in ways that challenge our current understanding of condensed matter physics. And we can't study them directly because we can't create conditions extreme enough to produce them, and we can't access Jupiter's interior to sample them. So Jupiter becomes a natural laboratory, a place where extreme physics occurs naturally, where matter exists in states we can only theorize about. Understanding these states requires combining observations, gravity measurements, magnetic field data, thermal emission, with sophisticated computer models that simulate conditions inside Jupiter. It's physics by inference, working backward from measurements to deduce what must exist beneath. As you drift into sleep, Jupiter's interior remains inaccessible, containing matter in forms we can't create or directly observe. States of existence that challenge our understanding, exotic phases that exist only under conditions impossible to achieve on Earth. The universe creates conditions everywhere that exceed our ability to replicate, teaching us that reality is more diverse than our laboratories can show. The color of Jupiter's storms remains partially mysterious. The Great Red Spot is distinctly reddish, sometimes brick red, sometimes more salmon-colored. But other storms, like the white ovals, are white. Brown barges are brown. Why these differences? The leading explanation involves altitude and photochemistry. The Great Red Spot towers higher into Jupiter's atmosphere than most other features, its clouds reaching into regions where ultraviolet sunlight is more intense. This UV light breaks apart simple molecules, ammonia, methane, water, creating reactive fragments that can recombine into more complex organic molecules. Some of these molecules are colored. Sulfur compounds can appear red or orange. Phosphorus compounds can produce various hues. Complex hydrocarbons, long chains of carbon and hydrogen, can range from yellow to brown to red, depending on their structure. The specific color depends on which molecules form, and that depends on the chemical inventory available, the UV intensity, the temperature, and other factors. The Great Red Spot's height means its clouds are exposed to more intense UV radiation for longer periods, allowing more complex photochemistry to occur. The resulting molecules accumulate, giving the storm its distinctive color. White ovals, being lower or less persistent, don't develop the same degree of coloration. Brown regions might represent areas where we're seeing through the upper cloud layers to deeper, darker material below. But this is still partly speculation. We don't know exactly which molecules are responsible for the red color. Spacecraft haven't sampled the Great Red Spot's clouds directly. instruments observe from above or from a distance, inferring composition from spectroscopic observations. The exact chemical recipe remains uncertain. The color also varies. Sometimes the great red spot appears more intensely red. Other times it fades toward pale orange or salmon pink. These variations might reflect changes in the storm's altitude, circulation patterns, or the availability of chemical precursors. As you drift off, the great red spot spins, its color shifting subtly over months and years, a storm whose appearance changes like a mood ring, reflecting internal processes we're still learning to interpret. Jupiter's magnetosphere isn't just a static magnetic field. It's a dynamic environment filled with electromagnetic waves, oscillating fields that ripple through the plasma like waves on water. These waves can interact with charged particles, transferring energy to them through a process called wave-particle interaction. When conditions are right, particles can be surfed by these waves, accelerated to relativistic speeds, velocities approaching the speed of light. The particles gain energy with each interaction, spiraling along magnetic field lines while simultaneously bouncing back and forth between Jupiter's north and south magnetic poles, all while being accelerated by electromagnetic waves. This natural particle acceleration is enormously efficient. Jupiter's magnetosphere creates radiation belts containing particles with energies that would require enormous particle accelerators to achieve on Earth. And the magnetosphere does it continuously, for free, using energy from Jupiter's rotation and the interaction between the magnetosphere and the solar wind. Understanding how this works has implications beyond Jupiter. Similar processes occur around Earth, around other planets, in pulsar magnetospheres, in active galactic nuclei around supermassive black holes. Wave-particle interactions are fundamental to plasma physics, and Jupiter provides an accessible laboratory to study them. But we don't fully understand all the mechanisms. There are multiple types of electromagnetic waves: Alfvén waves, Whistler mode waves, ion cyclotron waves, each with different properties and each capable of interacting with particles in different ways. Which waves dominate? How do they couple? How is energy transferred from planetary rotation to waves to particles? Juno's instruments measure these waves directly, recording their frequencies and amplitudes as the spacecraft passes through different regions of the magnetosphere. Combined with particle detectors that measure energies and trajectories, these observations are helping build a comprehensive picture of how Jupiter's natural particle accelerator works. As you rest, invisible waves ripple through Jupiter's magnetosphere, accelerating particles to enormous energies, an ongoing process that's been occurring for billions of years. Plasma physics operating on planetary scales. Nature demonstrating particle acceleration techniques we're still trying to replicate in our most advanced laboratories. The traditional picture of Jupiter includes a solid core, a sphere of rock and metal at the center, distinct from the surrounding layers. But Juno's gravity measurements suggest something stranger. The core might not be solid. It might not even be a distinct structure. Instead, Jupiter's center might be a fuzzy transition zone where core material is partially dissolved in the surrounding metallic hydrogen. Think of it like mixing sugar and water. At first, the sugar remains distinct, solid crystals surrounded by liquid. But as you stir and heat the mixture, the sugar dissolves, creating a gradient where the solution is more concentrated near the bottom and more dilute higher up. Eventually, there's no clear boundary between sugar and water, just a solution with varying concentration. Jupiter's core might be similar. Under the extreme temperatures and pressures at Jupiter's center, tens of thousands of degrees, pressures millions of times Earth's atmosphere, rock and ice might partially dissolve in metallic hydrogen. The result would be a large, diffuse region where core material is mixed with hydrogen, creating a gradient rather than a boundary. This fuzzy core could extend thousands of miles, containing several Earth masses of heavy elements dispersed throughout a volume much larger than Earth. It wouldn't have a surface you could stand on, or a distinct edge you could identify. Just a gradual transition from core-enriched metallic hydrogen deeper down to purer metallic hydrogen higher up. Why would the core dissolve? Perhaps it never fully formed as a distinct structure, or perhaps it did form initially, but was disrupted by giant impacts that mixed material and prevented reseparation. Or perhaps the extreme conditions simply make dissolution thermodynamically favorable. Rock and metal are soluble in metallic hydrogen, under these conditions the way sugar is soluble in water. If this is correct, then Jupiter's interior is even stranger than we imagined. Not just layers of different materials, but gradients and mixing zones, regions where the very concept of core or mantle becomes ambiguous. As you drift off, Jupiter's center remains fuzzy in both senses, uncertain in our understanding and perhaps genuinely diffuse in physical structure, a planetary interior that defies simple categorization. Earth has water, lots of it. Our oceans cover 70% of the surface, and there's more water locked in rocks and ice. But where did it come from? Earth formed in the inner solar system, where temperatures were high enough to vaporize water, preventing water ice from condensing. So how did Earth become a water world? One possibility is that water was delivered later, after Earth had mostly formed, by impacts from water-rich asteroids and comets. These impactors formed farther from the sun where water ice could condense. But how did they reach Earth? Many would have stayed in the outer solar system where they formed, unless something redirected them inward. Enter Jupiter. As Jupiter formed and migrated, its gravity stirred up the asteroid belt and outer solar system, scattering objects throughout the inner solar system. Some of these objects were ice-rich, asteroids containing substantial water ice, or comets from the outer regions. When they struck Earth, they delivered water along with other volatiles, like carbon dioxide and organic molecules. Jupiter might have been both destroyer and provider. Its gravity prevented Mars from growing larger, starving that planet of material. But it also delivered water to Earth, possibly making our planet habitable. Without Jupiter's influence, Earth might have remained dry, a rocky world without oceans, incapable of supporting life as we know it. This is still somewhat speculative. Measuring the isotopic composition of Earth's water and comparing it to different types of asteroids and comets helps determine where our water came from. The data suggests multiple sources, some from asteroids, some from comets, which fits the picture of Jupiter scattering various types of objects inward during the solar system's youth. So the water in your body, the water you drink, the water that makes up 60% of your mass, might have journeyed from the outer solar system, flung inward by Jupiter's gravity. delivered in violent impacts that simultaneously devastated and enriched the early Earth. As you drift towards sleep, hydrated and alive, Jupiter continues its orbit, billions of years after it helped create the conditions for life on Earth, indifferent to the consequences of its ancient gravitational influence. Jupiter radiates more heat than it receives from the Sun. We've measured this consistently for decades. But we've never directly observed where that heat comes from or confirmed the mechanisms that generate it. The leading theory involves helium rain, but it remains unproven. The idea is this: deep inside Jupiter, at depths where metallic hydrogen exists, helium and hydrogen can separate, like oil and water. Helium, being denser, forms droplets that sink through the metallic hydrogen, falling toward Jupiter's core in a literal rain of liquid helium. As these droplets fall, they convert gravitational potential energy into heat through friction, warming Jupiter from within. This process would be slow but steady, operating over billions of years. The helium gradually separates and settles, releasing energy throughout Jupiter's interior. Eventually, much of Jupiter's helium might accumulate near the core, leaving the outer layers depleted. Saturn might be further along in this process, which could explain why Saturn radiates even more excess heat relative to its size than Jupiter does. But we've never observed this helium rain directly. It occurs too deep to see, in regions no spacecraft can visit. We infer it from measurements of Jupiter's atmospheric composition: slightly less helium than expected in the upper atmosphere, suggesting depletion, and from heat measurements showing excess radiation. Computer models suggest helium rain is thermodynamically plausible under Jupiter's interior conditions, but it's not confirmed. Other mechanisms might contribute. Jupiter is still slowly contracting under its own gravity, and this contraction releases heat. Tidal interactions with the Sun and moons might generate some heat. Chemical reactions or phase transitions in the interior might release energy. The truth is probably some combination of processes, but we don't know the relative contributions. Jupiter's interior remains inaccessible, its processes inferred rather than observed. We build models, check them against measurements, refine them when observations don't match predictions. Slowly, patiently, we work toward understanding. As you rest, helium might be raining deep inside Jupiter, droplets falling through metallic hydrogen, a slow drizzle that's lasted billions of years, generating warmth through gravity, keeping Jupiter glowing faintly in the darkness, a process we believe occurs but have never witnessed. Orbits aren't eternal. Tidal forces, the same forces that heat Io and Europa, also cause moons to migrate over time. The direction and rate depend on whether a moon orbits faster or slower than the planet rotates. Moons orbiting faster than the planet's rotation gradually move outward, while moons orbiting slower spiral inward. Jupiter rotates every 10 hours. The Galilean moons orbit more slowly. Io takes 1.77 days, Europa 3.55 days, Ganymede 7.15 days, Callisto 16.7 days. This means they're all gradually spiraling inward, very slowly, as tidal interactions transfer angular momentum between Jupiter and the moons. But the timescales are enormous. The inward migration is measured in meters per century or less. At current rates, it would take hundreds of billions of years for any of the Galilean moons to spiral into Jupiter, far longer than the remaining lifetime of the Sun. So practically speaking, the Galilean moons are safe. Smaller, closer moons face different fates. Some of Jupiter's inner moons orbit close enough that tidal forces might tear them apart before they could crash into Jupiter. The Roche limit, the distance inside which tidal forces exceed the moon's self-gravity, means sufficiently close moons will be shredded, their debris forming additional ring material. The outer irregular moons have their own uncertainties. Their distant, elongated orbits are susceptible to perturbations from the Sun and other planets. Over very long time scales, some might be ejected from Jupiter's gravitational influence entirely, becoming independent objects orbiting the Sun or even being captured by other planets. So Jupiter's moon system isn't static. It's slowly evolving, with moons gradually migrating, some moving inward, others potentially escaping, all on timescales that dwarf human comprehension. Billions of years from now, the arrangement will be different. Some current moons might be gone, new moons might be captured. The dance continues, but the dancers change. As you close your eyes, the moons orbit patiently, their fates determined by tidal forces and gravity, slowly migrating along paths determined billions of years ago, heading toward futures they'll reach long after humanity is gone. Europa's ocean is one of the most tantalizing features in the solar system. A global sea beneath ice, potentially habitable, but completely hidden from view. We know the ocean exists through multiple lines of evidence. We know it's deep and extensive, but we don't know its fundamental properties. Is it salty? On Earth, seawater contains about 3.5% dissolved salts, mostly sodium chloride. Europa's ocean might be similar, salty water in contact with a rocky seafloor, minerals dissolving over billions of years. Or it might be fresher, if the ice shell effectively seals the ocean from the rocky interior, preventing mineral exchange. Or it might be extremely briny, concentrated salt solutions existing in equilibrium with various hydrated minerals. The salinity matters for habitability. Life needs certain chemical gradients and concentrations. Too salty and osmotic pressures become problematic. Not salty enough, and certain chemical reactions don't occur efficiently. Earth's oceans represent a middle ground that works for life, but we don't know if that's universal or if life could adapt to very different salinity levels. What chemistry occurs in the ocean? Is there a water-rock interface where hydrothermal vents might exist, creating chemical gradients and energy sources like Earth's deep-sea vents? Or is the ocean sealed beneath layers of high-pressure ice, separated from the rocky core, with no direct contact between water and rock? Are there oxidants, chemicals that can serve as electron acceptors in metabolic reactions? Europa's surface is constantly bombarded by radiation, which splits water molecules and creates oxidants like hydrogen peroxide. If these oxidants make their way into the ocean through cracks or convection, they could provide chemical energy for life. We won't know until we go there. Future missions might analyze plume material, drill through the ice, or send submarines into the ocean. Until then, Europa's ocean remains a mystery. Water we know exists but can't sample, chemistry we can model but not measure, a hidden sea that might be among the most significant bodies of water in the solar system. As you drift off, Europa's ocean sloshes gently in the dark, its composition uncertain, its chemistry unknown, waiting patiently for the day humans finally come to explore. Jupiter's radio emissions aren't uniform. They vary in intensity and frequency, sometimes bursting loudly, other times quiet. And curiously, some of these emissions are correlated with Io's position in its orbit. When Io is at certain locations relative to Jupiter and Earth, radio emissions intensify. This correlation was discovered decades ago, but the mechanism connecting Io's volcanic activity to Jupiter's radio voice remains incompletely understood. The connection probably involves Io's plasma torus, that donut-shaped cloud of charged particles surrounding Jupiter at Io's orbital distance. As Io erupts, it injects material into the magnetosphere. This material gets ionized and swept up by Jupiter's rotating magnetic field, which moves faster than Io orbits. The interaction between Io, the torus, and the magnetic field generates electromagnetic waves that propagate through the magnetosphere. Some of these waves are in radio frequencies, detectable from Earth. The exact mechanism for converting magnetospheric oscillations into radio emissions involves complex plasma physics, wave modes, particle resonances, electromagnetic coupling across vast distances. It's not simple radiation from accelerated charges. It's a chain of interactions involving Io's atmosphere, the plasma torus, magnetic field oscillations, and particle acceleration, all working together to produce radio bursts. The fact that volcanic activity billions of miles away can modulate radio emissions detectable from Earth is remarkable. It shows how interconnected Jupiter's system is. The moons aren't separate from the planet, but intimately coupled to it through gravity, magnetic fields, and particle exchanges. Io's volcanoes don't just affect Io, they affect the entire Jovian system, filling the magnetosphere with material, creating plasma that interacts with magnetic fields, eventually producing radio waves that travel across the solar system. As you rest, Io erupts, and somehow, through a chain of electromagnetic interactions we don't fully understand, Jupiter's radio emissions change, modulated by a moon's volcanic heartbeat, physics connecting solid surfaces to magnetic fields, to radio waves in ways we're still mapping out. Another reminder that planetary systems are webs of interaction, everything connected to everything else through forces invisible but undeniably real. Exoplanet discoveries have revolutionized our understanding of planetary systems. We've found thousands of planets around other stars, revealing that planets are common. Most stars have them. But are Jupiter-like planets common? The answer is complicated. We've found many gas giants, but they're mostly hot Jupiters. Giant planets orbiting very close to their stars, completing orbits in days rather than years. These aren't like Jupiter at all. They're in the wrong place, likely having migrated inward from more distant orbits after forming. We find them easily because they're large and close to their stars, making them easier to detect with current techniques. Jupiter-like giants in Jupiter-like orbits, distant, circular, requiring years to orbit, are much harder to detect. The detection methods we use, transits, radial velocity measurements, work best for planets that orbit quickly and pass in front of their stars frequently. Detecting a planet with a 12-year orbital period requires monitoring a star for decades to see multiple orbits, so we have observational bias. We see hot Jupiters easily, Jupiter analogs with difficulty. As exoplanet surveys continue, as we accumulate longer observation baselines, we'll learn whether true Jupiter analogs are common or rare. Early indications suggest they're less common than we might have expected, but it's too early to be certain. Why does it matter? because Jupiter might have played crucial roles in making our solar system habitable, deflecting some impactors, delivering water, preventing Mars from growing too large. If Jupiter-like planets are rare, then solar systems like ours might be rare. If they're common, then perhaps many planetary systems include giant outer planets that shape the inner system's architecture and habitability. As you drift off, thousands of exoplanets orbit distant stars, most unlike anything in our solar system, a few perhaps similar to Jupiter, creating their own gravitational architectures, possibly shaping the habitability of their inner planets. The universe contains multitudes, endless variations on planetary themes, and we're only beginning to catalog the diversity. Jupiter might be common or unusual. We don't yet know which. Don't yet know if we're typical or exceptional. We've studied Jupiter for centuries, through telescopes for 400 years, with spacecraft for 50. We've orbited it, probed its atmosphere, measured its magnetic field, mapped its moons. And yet fundamental questions remain. How did it form? What's its core made of? How deep are its storms? How much water does it contain? What chemistry occurs in Europa's ocean? Why is the great red spot red? Each answer generates new questions. Discovering Eo's volcanism led to questions about tidal heating mechanisms. Finding Europa's ocean raised questions about habitability. Measuring Jupiter's magnetic field irregularities prompted questions about interior dynamics. The fuzzy core revelation created questions about giant impacts and core evolution. This is how science works, not progressing toward a final, complete understanding, but deepening our questions, making them more sophisticated, more nuanced. We don't solve Jupiter. We develop richer, more detailed models. We replace simple ignorance with complex uncertainty. And that's okay. That's even beautiful. Jupiter doesn't need to be completely understood to be appreciated. The mystery is part of the appeal. Not knowing everything leaves room for wonder, for speculation, for the anticipation of future discoveries. Perhaps future missions will answer some current questions. Perhaps new technologies will reveal details currently hidden. Perhaps humans will eventually visit Jupiter, sending crewed missions to orbit and study the system directly, though that remains far in the future. Or perhaps some questions will resist answering for decades or centuries more. Jupiter is patient. It's been here for 4.5 billion years. It will be here for billions more. It can wait for us to figure things out, indifferent to our curiosity, spinning and radiating heat, regardless of whether anyone is watching or wondering. And maybe that's the final lesson, that the universe is full of wonders that exist independent of our understanding, that beauty and complexity persist whether or not anyone comprehends them. As you drift into sleep now, Jupiter continues its ancient orbit, storms spinning, moons circling, magnetosphere pulsing, a giant that holds mysteries as vast as itself, teaching us through what we know and what we don't, through answers and questions alike, a king of planets that reigns in the darkness, patient and eternal. And so we've journeyed through 100 facts about Jupiter, from its formation billions of years ago to the ongoing mysteries we're still working to solve. We've explored storms that rage for centuries, moons that might harbor life, magnetic fields that dwarf Earth's, and interior structures that challenge our understanding of matter itself. Jupiter is more than just the largest planet. It's a sculptor of orbits, a shield against impacts, a deliverer of water, a laboratory for exotic physics. It's a world that has shaped our solar system's history and continues influencing it today. Its moons might be among the most significant bodies in our search for life beyond Earth. Its magnetosphere teaches us about plasma physics that occurs throughout the universe. But perhaps most importantly, Jupiter reminds us of scale, of how small we are, how vast the universe is, how much remains to be discovered. When you look up at Jupiter in the night sky, you're seeing reflected light from a world more massive than everything else in the solar system combined. A giant attended by 95 moons, spinning every 10 hours in the darkness, 500 million miles away. And yet, for all its size and power, Jupiter is just one planet among billions in our galaxy, and our galaxy is just one among billions in the observable universe. Scale within scale within scale, each level revealing new complexities, new wonders, new mysteries. I hope these facts have given you something to think about as you drift off. Images of storms larger than Earth, oceans hidden beneath ice, magnetic fields stretching millions of miles, atoms arranged in forms impossible on Earth. Sleep well, knowing that the universe contains such wonders, that Jupiter spins on through the night, patient and eternal, waiting for us to understand it better, while remaining magnificent, regardless of whether we ever do. Thank you for joining me on this journey through Jupiter. Until next time, this is the Sleepy Scientist, wishing you clear skies and restful dreams.